get our inequality. So just 2-3 lines proof. And the equality case becomes true if the components of second fundamental form satisfy this expression, and these two equations, they give the expression for the corresponding shape operators given by this equation 6.2. So here one can see that this 6.3 means that, yes, please. Any question? This
Uh,
6.3, yes.
Sir, please
This,
try to conclude
okay,
within.
okay, okay. I
Yeah,
can see that I'm running out of time, but
yeah, yeah, yeah.
so what to do? Maybe a couple of minutes.
Yeah, sure, sure, sure.
Okay, so for example, you can see that this result for a Riemannian submanifold of a real space form, it was given by this inequality 6.5, but now the proofs are very easy to obtain, because in this case I can calculate this expression and this becomes C, so it is easy to handle. The similar kind of inequalities can be obtained for other kind of Casarotti curvatures using those four results for algebraic Casarotti curvatures. So, and then the same kind of things we can now apply for the submanifolds of complex space form. Here we have the idea of generalized complex space form, so which is an almost Hermitian manifold whose Riemann curvature tensor satisfies this expression. Of course, a generalized complex space form has some obstruction on the dimension. So the proper generalized complex space form is holding if and only if the dimension is 4. If the dimension is greater than 4, it has to be a complex space form. And here are different kind of submanifolds we have discussed here. But even if I just skip these things, recently I have put a paper on ResearchGate which deals with all these kind of different kinds of submanifolds of almost Hermitian manifolds, starting from 1955 to 2020. So a good survey could be obtained from that article. But here, the main result could be seen like this. The normalized delta Casarotti curvature, for the normalized delta Casarotti curvature, we obtain these inequalities for different kind of submanifolds, generic, theta slant, totally real, invariant, and then keep on changing the ambient manifold, and the inequalities are just being changed. So here is a list of the corresponding inequalities for Casarotti curvatures, and then here the equality cases are also being. I don't know what is, something is missing here. So, but the proofs are very easy. So, what I want to say that nowadays you can see that a lot of papers are appearing. They are choosing different kind of ambient manifolds and getting their Riemann curvatures in some well form, and then obtaining those inequalities by using some long techniques, and the proofs are spanned up to 10 pages, maybe 15 pages. But here one can see if I apply my techniques, then I can obtain those proofs in few lines, as you can see the present proof here. And the similar thing one can do for C totally real submanifolds or other kind of submanifolds of a Sasakian space form or Kenmatsu space form or generalized Sasakian space form or generalized kappa mu space forms, and people are doing those things, but in a long way. Even many of those papers, they are putting the references of a couple of papers what I wrote in 2016 and 17, but probably they are not using the results of those papers, and still they are proving their theorems by long way. but the results could be obtained in a very simple way, and I can end this. So here is the inequality for Casarotti curvature delta hat for a C totally real submanifold of a Sasaki space form given by 8.8. And one can see that the proof is just 2 lines, and it is so easy. And here is a problem to obtain inequalities for normalized delta Casarotti curvature. This for generalized Kaplan space form. Probably this problem has been solved by some because it needs a lot of calculations. But if I use these techniques, even I can obtain the proof in a very few lines. Here is the idea of centro-affine surfaces, hypersurfaces, where the Casarotti inequalities have not been discussed so far, and these results are being first time. I have presented this work in Denizli conference, but again I could not publish those results yet. But I am repeating those results here in this conference. So let Rn plus 1 be the affine space with a fixed point O, and the hypersurface is said to be centro-affine if the position vector of F is nowhere tangent to this. And then these are some formulae for, one can say the structure equations in one sense for centro-affine surfaces. And then under certain assumption, the equation of Gauss and Kodaji, and then some more. These terms are already known. It's nothing new. And here, this is a totally symmetric 0-3 tensor field C. And with these expressions, I can obtain the algebraic Casarotti, the inequality for algebraic Casarotti curvature for centro-affine hypersurfaces in Euclidean n plus 1 space given by 9.12. And here the equality cases are true if and only if these two equations are satisfied, and the proof I could prove it with the help of my result for Riemann vector bundle case or algebraic Casarotti curvature case. So these are the proofs. I think I can stop here. Thank you so much.
Thank you, sir. Thank you. I think you definitely need maybe 1 hour to present all these things. Yeah. But yeah, thank you very much for concluding in such a short time. So maybe just a small question, if any question or comment, a small comment from audience. If anybody want to ask anything or any comment.
Yes, please feel free to ask if there is any question.
I think we are running late also. So if anybody has any problem, maybe your email was already there, and they can interact, they can ask through email. So I think it's not a problem. So maybe I think I should hand over the charge of chairing the session. So thank you very much, sir. And thank you, Gauri Shankarji, for giving me this opportunity to introduce and to chair the session of Professor Tripathi. Thank you very much.
So thank you to both of you, sir, that you people have accepted my request and to be part of this conference. So especially Tripathi, sir, it is always our pleasure to host him in our conferences, seminars, workshops. So again, I am very much thankful to both of you that you people have accepted my request and also given talks, and Tiwari ji has also chaired the session. So with these remarks, since we are running late, next speaker to this session is Professor Mahendra Singh from Aishar Mohali, and he will talk on orientability in quantum theory. So to introduce Professor Mahendra Singh, I invite my colleague, Dr. Ashok Kumar Pathak. Please, Dr. Pathak.
Okay, thank you very much, sir. A very good morning to all of you. With immense pleasure, I would like to introduce Dr. Mahendra Singh, who is a great personality in the area of mathematics. Dr. Singh is currently working as an associate professor in the Department of Mathematical Sciences at IISER Mohali. He received his PhD degree in 2000 from Harishchandra Research Institute, Prayagraj, and after that he did postdoctoral fellowship from IMSC, Chennai. He started his academic career from IISER Mohali in 2012. Dr. Singh has published more than 40 research papers in various leading international journals of mathematics. Some of the well-known journals are the Journal of Algebra, Proceeding of Mathematical Society. He has received several awards like the Ambedkar Postdoctoral Fellowship, Inspire Faculty Award, Fulbright Nehru Academic and Professional Excellence Fellowship. He has also organized several workshops and conferences at various institutes. Dr. Singh has also delivered the various popular lectures, invited lectures at the various places of India and across the world. So, without taking much more time, I would like to invite today Professor Dr. Singh for today lecture. So, over to you, sir. Mahendra, sir.
Yeah. Am I audible?
Yeah, sir. So over to you, sir, please.
Okay. Okay. Thank you. Thank you so much. So yeah. Okay. So are you able to see my screen?
Yes, sir.
Okay. So because I'm using mobile data, the network problem, so I won't be switching on the video. I hope that's fine. Okay. So all right. So yeah, I will be talking about orderability in quantum theory. So since it's a short talk, I will just try to give some idea of the key terms, orderability, quantals, and the related thing. All right. Okay. So please let me know in case I become inaccessible due to network issue. Okay. All right. So the main thing that I'm talking about are knots and links. Okay. In the three space R3 and equivalently the three-dimensional sphere S3. All right. So what is a knot and a link? A knot or a link, it is simply an embedding of a circle or a bunch of circle, finitely many circles into R3. Okay. So you circle, you embed inside your R3 or equivalently S3. All right. And I don't want the situation where I have infinite number of crossings. So I assume that this embedding is smooth or piecewise linear. Okay. So I'm in a tame situation. There are people who also study wild knots. I am not getting into that. All right. So similar, let me just draw some pictures to give students some feel of what like this. So what I'm drawing is basically a projection of the knot. All right. So here is a simplest knot. What you can think of, you take a simple piece of string and tie the simplest knot and then close up the ends. The object that you get is looks like this in the three space. Okay. What I have drawn is actually a projection of that. All right. This is a trefoil knot. You can have many more. So you can also have, yeah. Look at this. So here I have two circles which are linked exactly once. So this is the famous half link. Okay, let me draw one more non-trivial one. Basically, these are the building this trefoil, and what I'm going to draw next. They are the building blocks for the whole subject of knot theory and also related three manifold topology. So this is what is the figure 8 knot. So I'm not really good at drawing, so please excuse me. Okay. All right. So yeah. So it has. You notice that it has four crossings. This one, this one, this one, and this one. All right. So this is a figure 8 knot. Okay. So these are like so these two knot trefoil and figure 8 are the prototypes of what is Thurston's classification. So trefoil is the basic of the torus knot. Figure 8 knot is the simplest of the hyperbolic knot. And there is another class of knots called satellite knots, which I'm not going to talk about. And the theorem, deep theorem, says that any knot falls in one of these categories. All right. So now what is the basic problem in knot theory is to classify knots. Okay, when two knots are equivalent. So I need to tell you what is equivalence of knots. So, or links. So I'm saying everything here for knots, but the same definition hold for links. Okay, link is simply embedding here disjoint union of finitely many circles. So the aim is classify knots or links, okay, up to isotopy, ambient isotopy. So what is an ambient isotopy is loosely, I mean, in some sense it is just wiggling around. So if you are given a knot in the trees hanging in the tree space, can you wiggle it around and get into and transform it into another knot? Okay, so that is what is isotopy is. I am not going to get into the formal definition. And the main theorem that one of the most influential theorem in this subject is due to Kurt Reidemeister. I think it dates back to 1926, also attributed to Alexander and Briggs, more or less at the same time. What does it say is that this problem of classifying knots and links in the tree space, which a priori looks a purely topological problem, is equivalent to certain equivalence classes of diagrams, which are basically four valent graphs on the plane. Okay, so two knots says that two knots are isotopic as embedded circles in R3 if and only if any regular diagram of one can be transformed into any regular diagram of the other by planar isotopies. So planar isotopies are simply wiggling in the planar. Like if you have a branch of a knot like this, then I should be able to straighten it up and make move in other form. As you can see, all of these are the same object. Okay, by planar isotopies. And the three Reidemeister moves. Of course, Reidemeister did not call them Reidemeister moves, so we call them Reidemeister moves nowadays. So three Reidemeister moves as follows. And these are the moves that will actually lead to the object called quandus that is mentioned in the title. All right, so what are the Reidemeister moves? So everything I draw here is a local picture. Okay, so first of all, let me explain what is a regular diagram. So regular diagram means you have a knot in the tree space and you project it on the plane with only very minor condition that the pre-image of each point is at the most 2 points. You should not have triple points, because if you have triple points, you won't be able to tell which arc is over, which is under, right? Which one is the middle one and so on. So you don't want that situation. And certainly you can do that because you perturb your knot a little bit in the tree space. Second condition is that the pre-image of a point should not be a corner. Of course, if you project it like this on the plane, then that will, you can call it a double point as well. So, but you can perturb the knot in the tree space and get rid of that. All right. That's what is a regular projection. Okay. So it's a very simple-minded definition. And the three moves are the following. Whenever you have a kink like this, you should be able to straighten it up. Okay. And this is what is the Reidemeister move one. Second one, if you have two arcs, one underneath the other, you should be able to, if you straighten them up, you should be able to transform it in this form. That is the Reidemeister move 2. And the third one is, if you have two arcs and a third one underneath on the upper side, okay, you should be able to bring it down. this one. This is the third right hemisphere move. All right, and these are all are very natural, right? In the three space, when you do it, you don't even realize that you are doing it. Okay, but if you are on the plane, because plane, then you are making crossing and you are changing the number of crossing and type of crossing. So we spell them out in the form of these moves. All right, and for those who know a little bit of quantum theory, this basically is the correspond to the third the braid relation, famous braid relation, which is physicists call the quantum Yang-Baxter equation. Okay, so this can be written algebraically. So these three moves will lead to what is an quantum. So let us look at this theorem again. It says that classifying knots is equivalent to classifying their diagrams up to planar isotopies and three right hemisphere moves. So now what I do is I will associate an algebraic object using these three moves, because these three moves are enough to if I'm able to work these moves out, then I can say about the knots, right? So let us set a rule as follows. Okay. All right. So suppose I have a knot diagram. Dk of a knot k. Okay. Just for your convenience, you just keep the trefoil in mind. Okay, this is your k. This is what I have drawn here is your d of k, because I have drawn it on the plane. Right. And now I set the rule. I orient it in some fashion. Okay, so like this is one, so I could put this orientation. So take a local picture around a crossing. Okay, like the circle, this circle region. So you have a situation like this. You will have either a rule of this form, or you will have a rule of this form, right? That's the only possibility at each crossing. So what I do is I label these arcs by some alphabets, okay, abstract symbols, and set the rule. Whenever I have, let us say y is an overcrossing, because this arc is going over, and x is an undercrossing, then the outgoing arc is a result of a binary operation between these two variables y and x, and what that I set as x star y. It will be some new alphabet, right? That I call as x star y. And if it's the opposite orientation, then I set it as x star inverse y. All right. And if you use this rule, then you see that the three right hemisphere moves can be translated in the following form. What does it tell you? So look at this. This was the first right hemisphere move. And I said that this is equivalent to straightening it up. But if you follow this rule, what does it tell you? That x, and because the over and under arc are the same here, it is x star x, right? Because after all, this move is telling you that this is the same as this. So the exam tells you that x star x is x. So you are getting a binary, you are getting an algebraic system which has some binary operation with idempotency condition. Let us look at the second right hemisphere move. This was my second right hemisphere move, and I have taken the oriented version of that. There are little checks required, but believe me, they are very simple if you follow the rules. So if you, here is y, here is x. If I follow the rule, then it is x star y. All right, and then this become x star y star inverse y. But what does the second right hemisphere move told you? It said that they should be just the same, y and x. So that means what you are getting is that this identity is same as x. So that is x star y star inverse y is same as x for all x and y whenever there is such a crossing. This is the second item. This is the second item move is algebraically telling you this. All right. Similarly, you can work out the third item move, and it's a little complicated diagram, but let me nevertheless draw for you. So I have drawn it in a little different form because I want to use this labeling, but it's the same R3 move. All right, this one. So, all right. So if we label them, let us say Z, Y, and X, and if you follow that rule, do apply the rule at each crossing that I told you in the preceding slide, what you get is that this one will be labeled as X star Y star Z. Remember that the brackets are very important here, because you don't know a priori whether it's an associative system. In fact, it is highly non-associative system. It is associative if and only if it's a trivial operation. All right. And what you will get is that after doing the same diagram chase here and doing the labeling, what you are going to get, this labeling will get as X star Z star Y star Z. Right. But this R3 move is telling you that these two diagrams are the same. Therefore, this should be same as this. Right. So what you get is this identity X star Y star Z is same as X star Z star Y star Z. Okay. So what I have got from a knot diagram, I have got an algebraic system which has a binary with a binary single binary, actually two binary operation. The inverse come from the first one. So you can just say the single binary operation which has the idempotency condition and which has a property that right multiplication by each element is a bijection because it has this inverse. All right, and which is right distributive. Okay, and that is what a quandle is. So I can now formally define what a quandle is. So a quandle is a non-empty set with a binary operation. Let us call it star. Star satisfying the following conditions. First, idempotency. Second, right multiplication by under this operation star by each element is a bijection. That is given X and Y in X, non-empty set X, there exists a unique Z in X such that Z star X is Y. Here I am saying that right multiplication by S is a bijection. That's what I mean, right? And third is it is right distributive. X star Y star Z is X star Z star Y star Z. Okay, all these things happen for all X, Y, Z in X. All right. So quandle is a very simple algebraic system which is a binary operation with these three axioms. All right. And you saw the star inverse somewhere in the preceding slide. That is what coming from the bijection, because if right multiplication by each element is a bijection, so the inverse one, what you get, you can call it star inverse. Okay. That's what in mom. So if there is any confusion, it's just implication of the second one. All right. So what you saw in the preceding slides is that this binary operation is coming very naturally from knots in the very topological objects. At the same time, these are abundant in almost every area of mathematics. So let me give some more. Let me first quote the famous theorem that that has actually revolutionized knot theory in the past decade. So famous theorem, and this was proved independently by David Joyce and Sergei Matveev. Almost exactly at the same time, actually, surprisingly, 1982. It was Joyce's thesis, and Matveev was anyway a very established knot theorist. So what they proved is the following, that this algebraic system that I will get out of knot, I will call it a knot quandle, okay, for obvious reasons. And they proved that it is almost a complete invariant. It is much stronger than the knot group, fundamental group of the complement. Okay, so two knots. In fact, much more is true for links, but I'm just due to time constraint, I'm saying it for knots. So two knots K1 and K2 are okay. So it's difficult to state it in this way. So let K1 and K2 be two knots. Then the knot quandles Q of K1, this is a notation that I denote for knot quandle, Q of K1 and Q of K2 are isomorphic if and only if either K1 is K1 is K2, it is isotopic. This equality here is isotopy, as you understand, or K1 is isotopic to. So I am taking oriented knot, by the way, as you can be to oriented knots. Okay, or K1 is isotopic to take the mirror image of the second one, right? That means simply change all the crossing the diagram and you get a new knot that you call the star. Let us not call it star to confuse, so a bar. And minus means change the orientation of the knot, like this. That's all. A very beautiful theorem. It is a very strong invariant. Believe me that for fundamental group it doesn't hold. It holds only for prime knots, and that's a famous theorem of Gordon on Luke. That fundamental group of prime knots completely classify the knots, and that's only for prime knots. But this theorem is in fact true for links. Okay, and this completely classifies. So now, therefore, this completely opens up a new direction. That if you want to study classify knot, you better understand quantas, these algebraic systems. Okay, and a huge amount of work has gone in there, and there is a well-developed cohomology theory, and in fact, it turns out that the cohomology theory for quantals is a very particular case of a very general cohomology theory for what are called solutions of quantum Yang-Baxter equation. So due to lack of time, I will not get, but I hope it's a good time to advertise that. All right, so now, so this is, I hope this puts things in perspective. Now let me give more examples of quantal, how they appear in other areas of mathematics. I hope I have some time. Okay, so some examples of quantals. Groups supply a rich, provide a rich supply of quantals. So if G is any group, okay, then you can define new binary operation, just conjugation. This one. And you can check it's a quantal. Okay, so groups are naturally quantals, and you can turn a group into quantal in a variety of ways, and they all are different. It's very hard to actually classification problem for quantals is much harder than groups. And one more example, of course, not quantal. So if K is a not, then QK is a quantal. And if you are wondering what this object is as a set, just like as you do for groups or in general in any universal algebra setting, QK is defined by generators and relations, and the generators of these are the arcs of your knot diagram, and the relations are exactly as I spelled out in the diagram. Whenever you have a crossing like this, okay, you know what the relation is. You know this y, this is x, and this is x star y. That's all. So it has a presentation, just like you have for groups or any algebraic system, nice algebraic system. Okay, and in fact, you can, or Riemannian symmetric spaces are also quantals. I don't know what the spelling is. Riemannian symmetric spaces can be seen as quantals because each point has an isometry which preserves that point, right? So using that isometry, you can define a binary operation which turns it into quantal. And even in nice algebraic groups can be turned into quantals. So I will not get into that. So the idea is that you can see that you can actually have this structure in almost any area of mathematics. Okay. So now coming to now the main thing, orderability. So with this, let us talk about orderability of quantals. Okay. Orderability. So this orderability, idea of orderability in groups has been studied for a long time, particularly for groups appearing in low dimensional topology. It has attracted a lot of attention. So a group is said to be left orderable. A group is said to be left orderable if there exists a total order, total linear order. Actually, I'm using both the terms. Sometimes total and linear means the same. Total linear order, this on the group G, which is left invariant. Okay. left invariant. That means, what does it mean? That is if x is less than y, that should imply that left, right? So zx is less than zy, okay, for all x, y, z in the group G. And similarly, you can define right orderability in a similar way, and you can also define biorderability. A group is biorderable if it is invariant under both left and right. And it turns out that figuring out whether a group, well, so let me give some obvious non-examples. Finite groups are never orderable, okay, neither left nor right, of course, then not biorderable, because of torsion, okay. So finite groups are not orderable, so this property is meant for infinite groups. Not orderable, neither left nor right, and also of course not biorderable. Of course, free abelian group is biorderable rather. Coming to topology, braid groups Bn, okay, they are left orderable. So exercise for student is, for groups left orderability is equivalent to right orderability, okay. So when I say left also, that means the right, but it doesn't mean biorderability, remember. So Bn are left orderable braid groups. And what is this connection with the topic we are talking about? Braid groups they have geometrical interpretation as right configurations of strings in the three space, and when you close them up, what you get is a knot or a link. Okay, so that's how they are connected to knots and links. In fact, if you take the infinite braid group and go modulo Markov equivalence, this classifies your knots up to isotopy. Okay, so that's the connection with knot theory. And also there is a representation of braid group into symmetries of the quandle, so that's how they are connected quandle. And pure braid group Pn, which is a subgroup of Bn, okay, is biorderable. It's a very highly non-trivial result of Peter de Horny, okay, so who actually set this business of orderability into limelight. Dale Robson and their group, okay, right. And many three manifold groups are known to be left orderable, biorderable. In fact, all knot groups are left orderable, I guess. Yeah. Let me be precise here. Yeah. They are left orderable. So all pi1 of R3 minus knot left orderable. But not all of them are biorderable. All right. So this orderability is a very well studied theme in group theory. So what we thought is that maybe we can talk about this orderability in this new algebraic system called quandles. But it turns out that it is not that straightforward because the binary operation there is non-associative. And the obvious reasons, the one-sided orderability does not imply the other. But the definition of orderability is the same, right? Because you have the same, the same definition. It's a set with a binary operation. So we can define orderability of quandles, or for that matter any magma or any set with a binary operation, right, of quandles in the same manner. Okay, so I'm not repeating the definition. That means if there is a total order which is left invariant for left orderability, which is right invariant for right orderability, okay, with respect to the star operation. And it turns out here that left and right do not imply each other, okay, for obvious reasons. So left orderability does not imply right orderability. So do I have some more time? How much time do I have? Hello? 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 Am I audible? And right orderability?
Yes, yes, sir.
How much time do I have? Okay, so maybe I will wrap up in 2 minutes. Okay, so orderability here is a little complicated. Left and right do not imply the other. And here I will just state one theorem of ours. It's a paper with Hitesh Rondal, a postdoc of mine, Manpreet Singh, my graduated PhD student, and myself. And it just appeared in Edinburgh Math Society.
Hello.
Yeah, do I have some time?
हेलो, मेरी आवाज क्यों नहीं जा रही है?
Hello. So if m and n are bigger than or equal to 2, such that they are not multiples of each other, then the torus link TMN is not right orderable.
Professor Mahendra?
Yes.
Try to finish within 3 to 4 minutes.
Yes, I'm done. I'm just take 1 minute. I'm done.
Okay, fine.
Okay, sure. Thank you. Okay, so we proved that the torus links under these conditions are certainly not right orderable, and we really don't know about left orderability here, and of course they can't be bi-orderable. But you might be wondering whether there are some knots and links which are orderable at all, and the answer is yes. So another theorem is that the figure 8 knot torus link quandle. I'm talking about quandles. Okay, the figure 8 knot quandle is left orderable. Okay, and the second is that the trefoil is neither left nor right. Trefoil knot quandle is neither left nor right orderable. Okay, so the situation for quandles is entirely different for link quandles. All right, and we also showed orderability of various other quandles which appear in different contexts in mathematics. So, but from knot theory perspective, this is our result. So I think I will stop here. Thank you.
Okay, thank you, Doctor. So, any questions, please, from audience? If you have any doubt, if there are any questions, feel free to ask. It seems there are no questions, yes, sir. So, on behalf of organizing committee, I am very much thankful to Professor Mahendra Singh that he accepted our invitation and delivered a nice talk in this conference. So, thank you, sir.
Thank you very much.
So, in this series, now we have two short talks. The first one will be by Dr. Sachin Kumar Srivastava from Central University of Himachal Pradesh, and the second one will be from Dr. Jaiprakash Singh from Mizoram Central University, Mizoram. And to chair these two sessions, I invite Professor Sudhir Kumar Srivastava from Deen Dayal Upadhyay Gorakhpur University, Gorakhpur. So over to you, sir. Yes.
We can start, Gauri Shankar.
Yes, sir. Yes, please. Yes.
Sachin is there?
Yes, he has joined.
Sachin sir is there. First.
He has joined just a few minutes ago. Dr. Sachin? He was Online, just I have seen.
Hello.
Yes, yes, he is there.
Sir, sir, I'm audible.
Oh, yes, yes, yes.
Yes, yes, yes.
So you are audible but not visible.
Yes, sir, I'm also visible. Yes, sir.
Oh, oh, okay. Again, welcome to all in this season. In this session, we have with us the young, energetic differential geometer, Dr. Sachin Kumar Singh, and I have a privilege to introduce him because he is my student as well as younger brother as well as my colleague also for 2 or 3 years. Too many relations with Sachin. Right? So he's a very good differential geometer and very good classroom teaching because he was our colleague for 2 or 3 years and he is very much popular among the students and which is the main quality of a teacher. So in this session, we have a talk of Professor Sachin Kumar Srivastava. He is the assistant professor in Central University of Himachal Pradesh. And you just go through his lecture and what I am saying about him, you can judge yourself. Sachin sir, you can start the lecture.
Sir, thank you so much, sir, for your nice words.
सचिन शेयर हो रही थी स्क्रीन शेयर कर
एक मिनट सर.
No, sir.
and both of you have 20 minutes for your talk, so be careful about the time also.
Hello, sir, I'm audible.
Yes, you are audible.
Sir, can I start?
Yes, yes.
Good morning to one and all present here. Many thanks to the organizer for inviting me in such an important conference. I feel privileged that my respected guru, Professor Sudesh Srivastava from Dindayal Upadhyay Gorakh University, is chairing our session. Thank you so much, sir, for your gracious presence. Thank you so much, sir. The topic of my talk is characterization of legendary curves in quasi-Sakian pseudo-metric three manifold. Actually, was just I want to tell the motivation about this, why I have chosen such topic. Actually, theory of curves has been active and interesting area of research since the beginning of the calculus. In particular, Isaac Newton was the first who presented systematic analysis of cubic curve, whereas gravitational waves were first predicted by Albert Einstein in 1916 as a part of his theory of general relativity. A parametrized curve is defined as a smooth map from open intervals, Rava's theorem lead to the have been carried out in contact geometry. It is very natural to ask what will be the characterization of such curves if they belongs to the pseudo-Riemannian geometry. So that's why I have chosen this topic. What I have done is I have
सचिन आपकी आवाज कट रही है.
yes sir, actually phone से connect हूँ actually.
Okay, go ahead.
So there are some basic introductions, some basic definitions. The whole topic is divided in legendary curves in normal normal almost convex pseudometric three-manifold, and I have denoted this by N3. And legendary curves in Q3, where I have denoted Q3 by quasi pseudo-Sasakian metric three-manifold, and the null legendary curves in Q3 and spherical legendary curves in Q3. Contact geometry is an important area of research with strong application in several fields. Almost contact geometry, which was revealed by Blair, represents an extension of Hermitian geometry to odd dimensions. A lot of publications were devoted to the study of almost contact manifolds, many of them being applied to the theoretical physics and mechanics and so on. The legendary curves in Sasakian manifold having the following properties: pseudo-Hermitian parallel mean curvature vector field, a pseudo-Hermitian proper metric curvature vector field in the normal bundle. In 2012, Inoguchi and Lee have studied legendary curves in normal almost contact metric three manifold, satisfying this condition, and gave natural equation for the planar bi-minimal curves. So now we start with the legendary curve. Actually, what is the legendary curves? Legendary curves is actually a one-dimensional integral submanifold. It's a curve. More precisely, suppose this is a manifold, almost contact metric three manifold. The integral curve of contact distribution, this distribution, is known as legendary curves. Means if this is the manifold, then the integral curve of this kernel eta is known as legendary curves. And this legendary curves is a very important curve that play a fundamental role in three-dimensional contact geometry. In the present study, we will focus on some specific legendary curves in quasi-Sasakian pseudometric three-manifold. This is actually basic definitions of spherical curves. When a curve is spherical, so as we know from the theory of curves and surfaces in Euclidean spaces, in three-dimensional Euclidean spaces, the curve is said to be spherical if and only if it satisfies this differential equation, where tau is a curvature and k denotes tau is a torsion and k denotes curvature, and dash is the differentiation with respect to the parameter s. So this is the well-known result that when a curve is said to be spherical. This is actually three-dimensional Euclidean space. We have tried to establish the relation when the curve is said to be spherical. We have in Q3 or N3, which manifold I have chosen. Now these are some basic definitions of the almost contact manifold. The main idea is if this is the condition for a spherical curve, for the curve to be spherical in 3 dimensions, then what will be the condition for a curve in Q3 or N3 to be spherical? And this is the integral representation of this differential equation. So almost contact manifold. So this is the basic definitions of at MBA is smooth paracompact odd dimensional manifold. Then M is said to be an almost contact manifold if the structure group, general linear group of tangent bundle is reducible to the UN cross 1. And this is equivalent of saying this satisfies these conditions. And this is the compatible metric and G, and the structure and this manifold together with this structure phi xi eta G is called an almost contact pseudometric manifold. And this is the normality condition when the manifold is normal, and this is an Eisenhower tensor. These are some other conditions. Now this is the some tools or results which will be used to prove this, to prove our motives. The first is an almost contact pseudometric 3 manifold. We have 3 statements which are equivalent. And this is actually nebula x phi y is given by this way. And let us denote by N3 a normal almost contact pseudometric 3 manifold. And log to N3 is called a quasi-pseudo Sasakian pseudometric 3 manifold, denoted by Q3. The quasi will be we will denote by Q3, and normal we will denote by N3. And these are the conditions when the manifold is Q3 or N3. And actually Q3 is a particular case of N3. So, and this is the an example of N3 normal almost contact pseudometric 3 manifold. We have constructed, we have chosen eta, xi, and so, and in such a way that it satisfies these conditions, and the structure is, and this structure is, the structure which I have chosen is an almost contact pseudometric 3 manifold. And we have denoted it by N3 epsilon. Epsilon is 1 or minus 1 according to the characteristic vector field is light like R, sorry, light like space like R, time like. When characteristic vector field is a light space like, then it is 1, otherwise minus 1. This is the example of normal almost contact pseudometric 3 manifold. This is a physical example actually. And this is a manifold normal almost contact metric 3 manifold. We have considered a curve, a smooth non-geodesic curve in this manifold, and then we obtained that the curvature and torsion are given by these formulas. So this is all about what is N3, what is normal almost contact pseudometric 3 manifold, and when we have chosen a smooth non-geodesic legendary curves in this manifold, then what will be the curvature and torsion of this. Now, these are some particular cases when in N3 the decomposition of characteristic vector field or re-vector field in the Fermat frame of non-geodesic Legendre curve is given by this way. And second remark is that when we be a non-geodesic Legendre curve in N3, then with J is parallel to the binormal, then N3 is quasi-Sasakian pseudometric 3-manifold. And third one is, let V be a non-geodesic Legendre curve in N3 such that J is parallel to the principal normal, then it has torsion alpha. In particular, the Legendre curve of beta Kenmatsu manifold with J space-like and parallel to N are circles. These are the known results. I mean to say that this is general result by which we can obtain the results till the date. Now, examples of Legendre curves in N3 epsilon. In first section, we have constructed normal almost convex pseudometric 3-manifold and defined a Legendre curves in that manifold and obtained their curvature and torsion. Now, these are some physical examples, some real examples. Suppose we have constructed this manifold N3 epsilon, and we have considered this curve V, which is given by this way. V1, V2, and V3 are components. Then this curve is the Legendre curve in this manifold if and only if it satisfies these two conditions. So this is actually the differential equation, non-linear differential equation actually, and there are so many solutions. So we can take the arbitrary solutions. Suppose we have chosen V1S, 1S0, means the Legendre curves will satisfy these two conditions. We have chosen an arbitrary curve V1S, that is very simple, 1S0, and we found that this Legendre curve curvature is this much and torsion of this Legendre curve is given by this much. Another arbitrary curve from that given differential equation is we have chosen V2 in such a way, and we obtained that the curvature of this is given by 1 and torsion is given by 1 by S square. Sorry. So first we have constructed normal almost contact 3 manifolds, and then we have obtained that the curve in this manifold is a Legendre curves if and only they satisfy these two conditions. We have taken the arbitrary solutions. We have chosen two arbitrary solutions. One is V1, this Legendre curve has curvature this much and torsion this much. And another is V2. Now question is that what will be the Euclidean picture of this? What will the Euclidean picture of this? As we know that the fundamental theorem of space curve, that if you know the curvature and torsion, then you can identify the curve. So we have curvature and torsion. So curvature and torsion. Then the Euclidean picture of these curves are first one, V1, is this much. When we have taken xi is space-like, then the curve is given by this way. If we take xi is a time-like, then the curve is given by this way. The same V1, the same V1, and the V1 is what is the V1? V1 is this curve, 1 as 0. But the Euclidean picture, when the xi is space-like, the shape is like this, and when xi is time-like, then space is curve is like this. And same for the second V2. The V2 we have chosen arbitrary. Then when xi is space-like, then curve is like this, and when xi is time-like, then the curve is like this. These are the differences. And these curves are made by Mathematica. And now, the decomposition of characteristic vector field means xi with respect to the frame v1, v2, v3 means one is tangent, second is normal, and binormal. In this frame, xi can be expressed like this way.
Sachin,
Yes, sir.
please finish within 2 minutes. You have already taken 5 minutes extra.
I have taken, sir.
I think it was up to 11.
Okay, sir. I'm trying to conclude as early as at earliest.
Yeah.
Sure, sir. Now these are some preparatory lemmas in N3. What is the preparatory lemmas? And these are the curvature and torsion of non-geodesic Legendre curves. Curvature and torsion. This is the theorem when the xi is expressed like this. Legendre curves in N3. This is a theorem for a non-geodesic unit speed curve in actually Q3. Q3 is a particular case of a normal almost convex pseudometric 3 manifold N3. With this much eta v dash is equal to m. If torsion is given by this and at one point these satisfy this condition, then v is a Legendre curve. This is the examples of Q3. This is the example of Q3 and this this is the non-geodesic Legendre curves in Q3. Actually, this is the physical example, and this is the curvature and torsion of this Legendre curves. 0.20, and now we have defined the null Legendre curves. Actually, null Legendre curves is given by this much. Arbitrary curve is said to be null curve if the metric is 0 for non-zero tangent vector. And for the null Legendre curves, we have obtained some results. And the lemma is that let V be a null Legendre curves in Q3, then V is a geodesic actually. Now the main result is in all the above sections we have constructed normal almost convex pseudometric 3 manifold and given physical examples of normal almost convex pseudometric 3 manifold. We have constructed the Legendre curves in these manifolds. Now the main section is that when these above Legendre curves are said to be spherical, in the next section we have derived the conditions that when the spherical curves are, when the curves, legendary curves are set to be spherical. And this is the result. This is the result. Actually, this is the main result. As earlier, I have said that, we know the fundamental result, that what is the necessary and sufficient condition for a curve to be spherical is that it must satisfy the condition 0.1. Analogous to this, motivation is this: what will be the condition for a curve to be spherical in N3 or Q3? Then we have obtained this result. Let V be a non-geodesic legendary curves in Q3 such that alpha is not 0 and V is non-constant if xi is space-like and satisfy this much, and if xi is time-like. Then the following statements are mutually equivalent. First, V is the element of Q3 is a spherical curve. Second, the centers of oscillating sphere at the point are the same constants and satisfy this condition. Means we have opted this condition when in this manifold curve is said to be spherical. Legendary curve is said to be spherical. This is the main result. These are some references, and thank you, sir. Yes, sir.
Thank you. Thank you, Sachin, for a nice talk and content. Conceptual, but it needs, I think, you can explain these in at least 1 and 2 hours, because
Yes,
there are so many conceptual things are there.
Yes,
because,
yes, sir.
Because in your first slide, when regular curve definition needs 30 minutes.
Yes.
Okay, but nice presentation. Well done. Thanks a lot. Our next speaker is Jayaprakash, sir. Dr. Jayaprakash.
Yes, sir.
Sachin, please you stop the share, then Jayaprakash sir can.
Yes, sir. Yes, sir.
Dr. Jayaprakash is in Mizoram University in Department of Mathematics and Computer Sciences. Right, Jayaprakash?
Yes, sir. Yes, sir.
Right, and I think long ago I am seeing Jayaprakash.
Yes, sir. You have evaluated one of my scholar thesis, sir.
Yes.
So you are very well known to me.
In Northeast region, it's we are very proud that we have a differential geometer in that area also. Jayaprakash, welcome on behalf of our organizer, also from CONIAPS, and you are in your department at present.
Yes, sir.
Okay. Then you can start your talk. You can share the screen.
Okay. Thank you, sir, for introducing me, and thank you, organizers, Professor Gauri Shankar, sir. He is very known to me since more than 10 years. So we are in good touch. So thank you, sir, for inviting me. So now I would like to share my screen.
Thank you.
So is my screen is visible, sir?
Yes.
Okay. Thank you. So today, title of my talk is on almost pseudo semi-conformally symmetric manifold. So I am going to talk about the geometrical property of pseudo semi-conformal curvature. So I will talk lots about the symmetries. So here is the outlet of my presentation. Introduction, existence of almost pseudo semi-conformal symmetric manifold and almost pseudo conformal symmetric manifold with non-zero constant scalar curvature and Kodachi type of Ricci tensor. Ricci symmetric almost pseudo semi-conformal symmetric manifold and Ricci recurrent almost pseudo symmetric conformal manifold. Einstein almost pseudo symmetric conformal manifold decomposability, and I will give two examples for supporting these theory. So starting with some introductory parts. So Riemannian symmetric spaces have an important role in differential geometry. So an n-dimensional Riemannian manifold M is called locally symmetric if its covariant derivative of curvature tensor vanishes, and this was introduced by Cartan in 1926. So a Riemannian manifold is said to be pseudo-symmetric if the curvature tensor, actually here associative curvature tensor, so of 0,4 type, satisfying this condition. Here nebula E R x y w is equal to twice A E R x y w plus A x R E y w plus A y R x E w plus A w R x y E plus G R x y w E rho. So here x, y, w, e are the vector fields. A is one form and rho is associated vector field, and it is defined ax is equal to gx rho. So G is Riemannian metric. So here if one form A is equal to 0, then this pseudo-symmetric curvature become this symmetric become locally symmetric. So a Riemannian manifold is said to be an almost pseudo-symmetric, and this concept is introduced by Ucide and Ghazi in 2008. If its associated curvature tensor of type 04 satisfy the following condition here. So you can see here one in the right hand side, one form is appearing as a B. So it is called almost pseudo-symmetric curvature. And here A and B are two one forms, and they are defined here. AE is equal to G of E rho, and BE is equal to G of E sigma. So here again rho and sigma are associated vector fields, and E is any vector field. So here again, if A is equal to B, so almost pseudo symmetric manifold will reduce to symmetric pseudo symmetric manifold, and if A and B both vanishes, then it reduces to locally symmetric. So now with this introductory part of symmetricness, this semi-conformal curvature tensor, this is introduced by Kim in 2016, and actually it is the linear combination of two curvature, that is conformal curvature tensor and panharmonic curvature tensor. So it is denoted by P tilde, So P tilde XYW is equal to minus N minus 2B C XYW plus A plus N minus 2B H XYW. So here A and B are constant, and both are not simultaneously zero. Otherwise, this definition is not valid. And here C denote the conformal curvature tensor, well known, and H denote the conharmonic curvature tensor. So moving to next. Here, if we take the inner product with vector field V, then we will get the this expression. This here it will be of the form 04 type. So you can see here. So here PxyWv is equal to Gp tilde xywv. Here P is curvature, actually semi-conformal curvature of rank 04, and P tilde is semi-conformal curvature of rank 13. And again here we can see if A is equal to B, A is equal to 1 and B is equal to minus 1 upon N minus 2, then semi-conformal curvature tensor reduces to conformal curvature tensor. And if A is equal to 1, B is equal to 0, then P is equal to conharmonic curvature tensor. So this semi-conformal curvature tensor is further studied by Kim in 2017, then UC Day and Su in 2018, and in 2019 Ali, and many more still studied on the certain geometrical properties of this curvature. So now some more definitions. So sir, I am audible?
Yes, yes. Please
You
go
are
ahead.
audible.
Okay, thank you, sir. So a non-flat Riemannian manifold whose semi-conformal curvature tensor P of type 04 satisfy this condition, nebula EP XYWV is equal to AE plus BE P XYWV plus AX PEYWV plus AY PXEWV plus AW PXYEV plus AV RXYWE. Then it is called almost pseudo semi-conformally symmetric manifold, and it is denoted in short form APSCS. Okay, so almost pseudo semi-conformally symmetric manifold. So now here is examples which support this curvature. So we have considered in 4 dimensions. So here the metric it is defined ds square, it is x1 plus 1 x4 square, here dx1 square plus 2 dx1 dx2 dx3 square plus dx4 square. Here x1 is not equal to minus 1. So here after using certain formulas and doing calculations, so we get here all non-vanishing components of Christoffel symbols, the curvature tensor and Ricci tensor as follows. Whatever it is shown, these are the values of non-vanishing Christoffel symbol and curvature tensor, even Ricci symmetric. Other which are not appearing, it means all components are 0. So from here further, due to some calculation and using formula, we can see here the scalar curvature is 0. So then we can define here by using all those non-vanishing and vanishing terminology. So we can see here this semi-conformally curvature tensor in this form. This is non-zero, and if we take the derivative, covariant derivative, so it come half a by 2, a half a. So this is non-zero because we have chosen a as a non-zero. So and then we will set the one forms AI and BI in this form. Here AI is equal to 1 over 6 x1 plus x1 plus 1 for I is equal to 1, otherwise it is vanishing, and BI is equal to 1 upon 2 x1 plus 1 for I is equal to 1. So here again with this we can show that the considered example is example. This is almost pseudo semi-conformally symmetric manifold. So next we can see this example also proceeding in the previous example manner. We can show this metric where ds square is equal to 1 plus 2q dx1 square plus dx2 square plus dx3 square plus dx4 square, where q is equal to exponential x1 upon k square, where k is non-vanishing. So we can easily show that this considered example is almost pseudo semi-conformally symmetric manifold, and here in this case the scalar curvature is vanishing, but in the previous scalar curvature was, here it is non-vanishing, and in the previous example it was vanishing. So next we will move to some result related to this almost pseudo semi-conformally symmetric manifolds. So here we have considered an almost pseudo symmetric semi-conformally manifold with non-zero constant scalar curvature and quadratic type of Ricci tensor. So here suppose if this condition actually I am just omitting all the proof and everything, just I will highlight the whatever the result we have obtained in the paper. So the theorem is in an almost pseudo semi-conformally symmetric manifold, the scalar curvature is a non-zero constant if and only if this condition satisfied, provided a plus n minus 2 b is non-zero. Then next, the Ricci tensor S of type 02 on a Riemannian manifold is said to be quadratic type if it satisfies the condition nebula xs yz is equal to nebula zs yx. Here S denote the Ricci tensor, x, y, z are the vector fields, and nebula is covariant differentiation. So this is the definition of quadratic type Ricci tensor. So assuming that the Ricci tensor is of quadratic type in almost pseudo semi-conformal symmetric manifold. So this next, actually this is the this gives this expression. So we know the Bianchi second identity in Riemannian manifold. So it is just similar to that. So the theorem says if the Ricci tensor in almost pseudo semi-conformally symmetric manifold is of constant quadratic type, then the semi-conformal curvature tensor satisfies the Bianchi second identity. So next theorem is in almost pseudo semi-conformally symmetric manifold, if the semi-conformal curvature tensor P satisfies Bianchi second identity, then it reduces to a pseudo semi-conformally symmetric manifold, provided these conditions hold. So next theorem is in almost pseudo semi-conformally symmetric manifold, if the semi-conformal curvature tensor P satisfy Bianchi's second identity, so that we have already proved in the previous theorem, then the scalar curvature is constant provided A plus n minus 2b is non-zero. So here is one proposition. If Ricci tensor in almost pseudo semi-conformally symmetric manifold with non-zero constant scalar curvature is of Podaji type, then it reduces to a pseudo semi-conformally symmetric manifold provided A plus n minus 2 b is non-zero. So next is a Ricci symmetry, almost pseudo semi-conformally symmetric manifold, and Ricci recurrent almost pseudo semi-symmetric manifolds. So a Riemannian manifold is said to be Ricci symmetric if its covariant derivative of Ricci tensor is vanishing. So nebula S is equal to 0. So suppose our considered manifold is Ricci symmetric, then after calculation actually we will get this expression A plus n minus 2b or n plus 1 ax plus bx is equal to 0. So hence we can state the following theorem. So in a Ricci symmetric almost pseudo semi-conformal symmetric manifold, the vector fields corresponding to one forms A and B are in opposite direction, provided R is not 0. So A plus n minus 2b is non-zero. So here is one corollary. So it says about in a Ricci symmetric manifold, almost pseudo semi-symmetric manifold, the scalar curvature vanishes if n plus 1 ax plus bx not equal to 0, provided a plus n minus 2b is non-zero. So next is a manifold is called Ricci recurrent if the Ricci tensor satisfy this condition. Okay. So here H tilde is non-zero one form. So assuming that the considered manifold with non-vanishing scalar curvature to be Ricci recurrent, and after simplification we get this this H tilde E is equal to thrice AE plus BE. Here H tilde, as it is already mentioned, it is a one form, non-zero one form, and AB are, yeah, B is also one form, already discussed, and E is a vector field. So we have a theorem. So in a Ricci recurrent almost pseudo semi-symmetric manifold, if the scalar curvature is non-zero and A plus n minus 2b is non-zero, then H tilde E is equal to thrice AE plus BE for all vector field E. Now Einstein almost pseudo-symmetric conformal pseudo-symmetric manifold. So a Riemannian manifold is said to be Einstein if Ricci tensor is proportional to the metric. Okay, can you see from here? Yes, sir.
नहीं करिए
Okay. An example of Einstein manifold can be seen as a vacuum solution of Einstein equation. It is given here. So suppose Ricky tensor is given like this: S Ex is equal to R by N Gex. So R is a scalar curvature, N is the dimension of the manifold, E and X are the vector fields. So then in Einstein APS-CS considered manifold, we have these relations. So if A is non-zero and the considered manifold is Einstein, so we get this some results here. If an Einstein almost pseudo conformally symmetric manifold is pseudo symmetric, and the condition 2a n minus 1 minus b n minus 2 is non-zero, and 3ae plus be is non-zero, then its scalar curvature vanishes provided a is non-zero. And if the scalar curvature vanishes in Einstein APS CS, then we obtain the result like if A is not zero and scalar curvature vanishes in Einstein almost pseudo semi-conformally symmetric manifold, then such a manifold is almost pseudo symmetric. So further some more results here. If the vector field rho1 defined by GE rho1 is equal to BE minus AE for all vector fields E is parallel vector field in an Einstein APS-CS with A is not with A is non-vanishing and rho1 norm of rho1 square is non-zero, then it is almost pseudo-symmetric. So we move to the last section of this decomposability of almost pseudo semi-conformally symmetric manifold. So a Riemannian manifold is said to be decomposable or product manifold if it can be written as m1p into m2 n minus p. Here p lies between 2 to n minus 2, that is in some coordinate neighborhood of Riemannian manifold. And here the corresponding metrics are given here. ds square is equal to gij dxi dxj, and that is equal to g bar ab dxa dxb plus g star alpha beta dxa dx alpha dx beta. Here g bar ab are function of x1 x2 xp and denoted by x bar, and g star alpha beta are function of xp plus 1 xp plus 2 and so on, and denoted by x star, and abc run from 1 to p and alpha beta gamma run from p plus 1 to n. So after considering this product manifold, we got this result. So let an almost pseudo semi-conformally symmetric manifold be decomposable. So
time.
Okay, just last slide, sir. Then Mn is equal to M1p cross M2 n minus p. Then the following results hold. So in the case if A and B is equal to 0 on M2, the manifold M2 is Ricci symmetric and scalar curvature R star is constant in M2 provided dr bar E star is equal to 0 and the condition hold. When M1 is semi-conformally flat, then M1 is an Einstein manifold. Okay, and these are the some more related results. Okay. These are my references. Thank you.
Thank you, Jayaprakash sir. Jayaprakash sir, at present you are head also, I think.
Yes, sir.
Yes. That I forget actually.
Okay.
Presently he is the head of department in Mizoram University also, right? And
Yes, sir.
more than going to be touch the half century mark in publication in near future. More.
Okay. With your blessing, sir.
Yeah, yeah. Also, he has four PhD scholar have completed, na? 4 or
No,
5?
sir. Five completed and
5.
one submitted, sir.
5 completed. Right. Four PhD scholar completed their PhD under his guidance, and main thing is that he never forget his subject, means differential geometry. Whatever the Oja sir has conveyed is just अभी तक पकड़े हुए हैं ओझा सर के हमारे पास दो बहुत अच्छे स्कॉलर, एक जयप्रकाश जी और हमारे भागवत जी हैं, जिनको हम लगातार देखते रहते हैं. So thank you for giving the lecture, and it is very fruitful for because the concept of whenever you apply the concept of semi, whether it is conformal, semi concircular, semi projective, whatever, so it is much fruitful for the new researcher because they can learn from there how to calculate how the calculation can be done. It is the easiest path for getting some hint. मतलब कैलकुलेशन सीखना है तो आपको वहां से सीखिए तो सबसे आसान चीज हमें लगता है वहां से पड़ती है. Thanks a lot, and thanks to Gauri Shankar sir also. He is busy in teaching, busy in all types of academic work, and one thing I say for Gauri Shankar sir, कि whenever he select the speaker, he is very much careful, because I have gone through so many lectures. Even if an assistant professor is giving some lectures, I think he is very carefully selected him. Because I got through some lectures in that program in previous month, when two husband and wife is there from ISER. So congratulations to Gauri Shankar sir also. If you want to, if any differential geometer want to learn something, they should have close relation with Gauri Shankar sir, because he's.
Thank you, sir. You are so generous to me.
No innovative. And
Gauri Shankar sir is multidimensional, sir. Yeah, he can manage so many learned speakers, sir. I am also very much surprised how he's
yes, so
he's
many
very hardworking, sir. I know.
so
I
many
told him,
different type of professors on same platform. It is the great
yes,
achievement.
sir. Even last 2 months back when Nasi program was there, so
Nasi
many
program is very
speakers
effective
were
and
there.
very much fruitful for our student also.
Yeah. Especially for new learners, it's very nice.
Very nice.
I always ask my student to join his program.
Sir,
thank you.
I have advanced invitation to you people for RMS next year.
Thank you.
Next July we are conducting RMS, 37th RMS. So it is already on the site of RMS.
Okay.
RMS or IMS?
RMS.
अच्छा, Ramanujan Mathematical Society.
Yes.
Very good. Badai, congratulations. But
so from when, sir?
In July.
It is in July.
Okay.
Next year.
Okay. Thank you.
Okay, congrats again to whole team of Central University of Punjab for organizing such a nice conference, and there are so many sessions up to I think 6:15 p.m. today also.
Yes, yes, yes. And then after that, we will have valedictory section.
Oh, okay, okay. Thanks a lot. So should I let, because we have admission and then 1:10 we have a class also.
Thank you, sir. Thank you.
Okay, thank you, Gauri Singh. Thank you, Jayaprakash sir.
Okay, thank you, sir.
So thanks to all of you for joining this session, and have a lunch, and after lunch we will start with the two talks. First one will be invited talk by Professor Karun Das from University of Delhi, and that will be related to topology. And next will be plenary talk by Professor John Parker from University of Durham, England, and that will be related to geometry. So I hope that these two will be very wonderful talks. And after that, this will be followed by some paper presentations, and of course, in last we will have the lecture session. So please have a lunch and join around 1:45 because next lecture is scheduled to be from 1:50 p.m. So thank you again, and please join us after lunch. Thank you.
Hello, Guruji, am I audible? Hello. Hello, am I audible?
Yeah, you are.
Yeah, hi.
Hello.
Hi, hi.
Good afternoon, sir.
Good afternoon, good afternoon.
Good afternoon.
Hello, Professor Karan. Good afternoon.
Hello, how are you?
Hi.
Hello.
I hope I am audible.
Yes, yes.
Thank you.
Hello.
Yeah.
Yes.
Am I audible?
Yes.
Good afternoon, sir.
Good afternoon. Let me join my mic.
Should we proceed or wait for 5 minutes?
Am I audible?
Yes, sir. Yes.
Okay. Thank you.
So, good afternoon to everyone. In this session, we have first plenary talk, invited talk by Professor Tarun Das from University of Delhi, and he will talk on some topological entropy in the nanometric system, etc. And to chair this session, I invite my friend Professor Prabhakar from IIT Roper. So over to you, Doctor.
Yeah, hi. It's my pleasure. Thank you. And it's my pleasure also to introduce Professor Tarun Das. Professor Tarun Das joined the Department of Mathematics, University of Delhi in, I think, February 2014. In fact, prior to joining this university, he was also working as professor at Faculty of Science, the Maharaja Sayaji Rao University of Baroda. In fact, his main research interests are including compactifications and absolutes, and even topological and differentiable dynamical systems. He completed his PhD from Allahabad University, and of course, he is having many awards. And to name few, in fact, he was research professorship in 2011 and also research fellowship during 2007 for collaborative research work at the Chungnam National University, South Korea. And also he was an active member in National Board of Higher Mathematics, and he has also research scholarship at School of Mathematics from TIFR Mumbai. He also organized many conferences and workshops, which also include very well-known ICTS programs. And also he was an active member, and in fact he even sponsored MTTS programs of NBHM. And in fact he was involved in 2010, 2011 of MTTS. Even at the time when he was working at Shayaji Rao University at Baroda. In fact, he is also a editorial board member of various journals, and one of them is recent trends in ergodic theory and dynamical systems, and also contemporary mathematics, which is American Mathematical Society journal. And of course, he is giving various lectures at different conferences, and he's very active in his research. And he is also presently serving as honorary treasurer of the Indian Society for History of Mathematics, and has served as sectional president of mathematical section of Indian Science Congress Association. So with this, I will stop the introduction, even though, of course, many things to say, but let me, he is going to talk on topological entropy in dynamical systems and recent advances. So over to you, Professor Tarun. Thank you.
Thank you, Professor Prabhakar and Professor Gauri Shankar both. Professor Prabhakar for saying so many things, but it wasn't essential. And also special thanks to Professor P.N. Pandey, who really he was my teacher when I was a student at University of Allahabad. I was doing my masters there, and Professor Gauri, because at the 11th hour yesterday I had to request him that I am unable to do it because I lost one of my very senior colleague here, who was a very distinguished scientist of our country from biochemistry, Professor J.P. Khurana, who was a sitting INSA vice president. But then in the yesterday evening, he said that if I can speak, I said, well, I have to. It's my duty. And thanks for reorganizing things. And I hope I can do something for this. Thank you all for this opportunity. Yeah. What I was planning initially was to talk about what we are currently interested in. A lot of global dynamics have been explored and in various parts in various ways, but there was some kind of point-wise stability, expansivity, and various kind of things. This was initially initiated sometime in early 70s, 1970s. But then a lot of work is currently being carried out by various mathematicians and various institutions, including there is a very active group at IMPA, Brazil, which is of course a good center for dynamical systems. We have some kind of collaborations with them. So I would like to reach up to that point, but I thought because it could be a mixed kind of an audience. So there could be some students also. So I thought to give a kind of a preliminary illustration of what it is, how it is. I'll make an attempt for that. I'll then try to talk about briefly what entropy is from the ergodic theory point of view. I'll use my Microsoft whiteboard for that, and then come to the topological aspect of entropy, which I have made some slides on that, and then possibly touch upon what we are trying to do. So that's a whole that's the way I have distributed. I've tried to. So okay, let me present my screen. Okay, let me. Okay, is the screen visible to everybody?
Yes. Now it is visible.
Thank you. Thank you. So, one aspect which is most important and have been at the is a pivotal to the whole development is a recurrence and some historical perspective. So, studying dynamical systems have helped immensely in understanding various natural systems and has helped in crafting numerous man-made systems to further understand our surroundings better. Right. So, it's all about the concept of recurrence was first introduced by Poincaré, who was during 1854 till 1912, a French mathematician. It was in his 270-page memoir published in volume 13 of Acta Mathematica in the year 1890. This, of course, had a previous version which was published not that way, but in the year 1889, a year before. And to my utter surprise, when I was looking at all this, the very early stages of my study in the dynamical systems, he was aware of presence of homoclinic points and things like that. Even in that time, of course, the homoclinic points and other things, related things, have been explored much later, 1960 and beyond, and after that. But he was aware of that, and of course, the chaotic behavior in the dynamical system. The recurrence theorem is he actually gave Poincaré gave a main theorem in his early days, which was a starting point. The recurrence theorem is a qualitative in nature and explains that almost every orbit in a dynamical system with finite invariant measure comes back infinitely many times to any point measurable set which is visited at least once. Orbit is like you repeatedly hit through a design configuration or a function map, continuous map, homeomorphism, measurable transformation, and so on and so forth on a space over whatever configuration we have. To be precise, it states that for a measure preserving transformation T over a probability space for E in a set in a member in script B with positive measure, we will find a subset F which is again measurable and equals measure of the set E and a sequence such that the repeated occurrence, so repeatedly T and I you are operating at the point X for each I and for each X belongs to F. So that will keep on visiting the set F. That will keep visiting the set F. So that's the recurrence process. That's the recurrence process which keeps happening. Yeah, just a minute. I wanted to. Is my screen very small now, or is it okay? Still, fonts are okay.
Maybe you can make it full screen.
Just a minute. I just wanted to be.
Control L.
No, that I know. That I know.
Yeah.
I'm just trying to make it. Yeah. Yeah. So yeah, that's so. Another important feature is hyperbolicity. We have interest in the study of hyperbolicity of invariant sets. We have some research in that. Particularly, we are interested in the study of hyperbolicity of homoclinic classes. That's what we are on: compact manifolds, C infinity manifolds, differentiable manifolds. Hyperbolicity for some of you, like those of you who are a student, for example, one can take a 2 by 2 matrix, integers entries, determinant 1, acting on, they'll carry on an action on the circle, for example, a torus. And yeah, then you can look at the eigenvalues. And if the eigenvalues are not equal to 1, greater than 1 or less than 1, but not equal to 1, then the action, if you look at it, will have the nature of expansion and nature of shadowing. It will trace orbits very well, and they are actually known to be hyperbolic. So yeah, that's a simple example. And of course, this can be generated over any n-dimensional torus. So yeah, so we have been interested in this, and for example, we have studied hyperbolicity of C1 persistently continuum-wise expansive homoclinic classes. So continuum-wise means instead of points, you are looking at continuums. Continuums means it could be small arc, for example, right? So it's a compact connected subsets of which are whose diameter is not zero, positive diameter. So yeah, something like that. So yeah, but these invariant, ultimately we are interested. One is interested in the invariant sets, for example. In invariant sets, even on a C infinity differentiable manifolds and all that, once we are working in that very nice scenario, invariant sets may not be carrying a differentiable structure. For example, Cantor set could be invariant subsets, and horseshoe, for example, can be invariant sets. So they are purely topological in nature, of course. Yeah. So, and yeah, of course, I can't get into the definitions of those things, but invariant sets, they carry importance, and but they may not. What my emphasis is that they may not carry the differentiable structure. So it's more important to look at those structures from the topological angle, from the measured theoretic angle, and so on and so forth. Right. So yeah, and it was Hadamard. Surprisingly, again, it was a surprising aspect to me when I noticed it first. Who studied first time hyperbolicity while studying geodesic flow on the unit tangent bundle of a surface of negative curvature. The above work, due to Hadamard, is also considered to be the beginning of symbolic dynamics. So I'll come to symbolic dynamics the moment I'm trying to talk about entropy. There on the symbolic dynamics, I'll talk about that. And it was Headland who along with Morse, who together published a a 50 plus page paper entitled Symbolic Dynamics in American Journal of Mathematics in 38. From there on, this area has been researched extensively, and today, of course, it's one of the most applicable areas we all know. Studying quantitative aspect of recurrence led to the ergodic theory. First independently proved results, that is ergodic theorems, are due to Birkhoff and von Neumann, established in way back in 1931. Then mathematicians started looking at the challenge in studying rate at which the given orbit returns very close to itself. They very rarely come back to exactly on itself, but very close to itself. Interesting results has been obtained in relative recent times on these aspects also. Another thing which I wish to uh, touch upon is the Hillel Furstenberg. Furstenberg, it was in 67. We all know he has been recently awarded Nobel Prize last year along with Margulis for their researches in the area of ergodic theory and dynamical systems. So he published a fundamental work in the first volume of Journal Math System about the disjointness, ergodic theory, and topological dynamics. So, and then of course, yeah, we were fortunate to have it in one of the conferences which Professor Prabhakaran was mentioning at Baroda. He, along with his wife, visited us for 4 or 5 days. And so this is the concept, on a compact metric space, for example, if you take a homeomorphism where you define a number nuv, f and u meet v is non-empty, the collection of all such integers. So we are looking at recurrence, how many times it comes and meet. So these are non-empty open sets. And system XF is topologically transitive if there is a dense orbit, minimal if the orbit is dense, and weakly mixing if the system is topologically transitive. Now, these notions are very closely and effectively related. And we say it is weakly mixing if NUV, where U and V are open sets, as I have just now defined, forms a filter base. And it is weakly mixing if it is thick in Z. So thick sets we all know, and in a set of integers. So if thick sets and thin sets, so we know that. A compact dynamic system is weakly mixing if and only if NUV is thick for every pair of non-empty open sets U and V next. This was something, this is one result which I am just quoting out of it. So out of many, which has been of greater, impact on this. So he has carried out a systematic study of transitive systems by introducing disjointness notion. This is indeed a fundamental contribution, as it has been instrumental for many related research. So I want to talk about topological entropy, but before talking about topological entropy, I just want to talk about entropy when it has come originally in the form of ergodic, in the ergodic theory. So I'll just go to my Microsoft board for a moment. Allow me that. Uh, Sorry, uh, just a minute. Yeah. Okay. I hope this is visible. Yeah. So this entropy notion. Okay, we all know Cantor set, and we all know that set of all bisequences over a over a say set bisequences of 2 digits. For example, I'm talking of this. So this is, and then one can think of 3 element set, for example. So this is also Cantor set. This is also Cantor set. So they are homomorphic and so on and so forth. But one can think of shift maps. So if you have a sequence by sequence and you shift everything to the one stage right, so that's a right shift, and to the left shift, and right shift and left shift. So these are left shift operators and right shift operators. So this is a starting point of symbolic dynamics and things like that. So that's which I said sometime back in one of my previous slides. So it was in 1943. They, the shift map, as I am saying, these two shift maps. So they were having a countable Lebesgue spectrum. They were understood to have countable Lebesgue spectrum, and they were therefore spectrally isomorphic. They were spectrally isomorphic. So the question was what differentiate them, though prima facie they looks like different, but what? So spectrally they were isomorphic. Are they conjugate also to each other? That was something which was explored, and it was in 1958. Uh, Kolmogorov, he actually introduced the notion of entropy. He introduced the notion of entropy in this, and he actually could prove that this this. So suppose I am calling this system as, say, this is x half, and this is, say, x. So okay, let me write it x2, and this is x3. That is better. So system x2 and system x3 have entropies log 2 and log 3, and that was the turning point. And it was proved that they cannot be conjugate, because conjugate systems have to have the same entropy level. So that was, and his work was slightly made. So they are jointly attributed to this. This was Siani. So Kolmogorov-Sriani, they actually introduced this notion of entropy, and to actually define entropy, one talks about entropy of entropy of a point, on a subalgebra. First of all, one defines entropy, then entropy of a transformation is defined, and then of course entropy of the whole T, whatever T. So these are shift maps, so one can define. So I'm not going to the definition. I'll quickly go to the definition of topological aspect when I come to that. So yeah, this was possible. This was made. This was the starting point of introducing entropy there. Uh, some examples, like one can think of rotation of a compact uh, abelian group. Of course, compact metric abelian group. So compact metric abelian group has entropies, has zero entropy. For example, rotation of unit circle, right? So this can be, these are some simple examples. I'm just trying to say, many of you might be aware. So that just to give you a feel. So any ergodic transformation with discrete spectrum also has a zero entropy, for example, right? So these are some simple things. And then one can, as I'm talking about the earlier, x2 is a 2 shift, x3 is a 3 shift. So you can think of a k shift, for example. So one can consider Markov shift and compute the entropy of the Markov shift also. So these are many things were studied along that line. And it was like, then the question was, how good is that invariant entropy? How good is this invariant as an invariant? Is it a complete invariant, for example? So complete invariance means if both if you have transformations capital T and capital S, if they have the same property, if they have property P and they are complete invariant, for example. So they are equivalents. If they are equivalent for a property P, then you say it's a complete invariant, which is not the case with the entropy, for example. So entropy is not in general enjoying this property. It's not complete invariance property. For example, another quick set of examples, like for what we can look at is, you look at T from unit circle to unit circle. So one dimensional torus, K to K. Tz is Az. A is again a member of K, and this should be dense. Right, it's dense in K. And similarly, one can think of another B, something like that. So you have two operators, S and T. Suppose you have this operator. the entropies are, one can compute the entropy, and they are found to be zero entropy. If the group, suppose I'm calling this as this G and this is say H, for example. If G is not equal to H, if G is not equal to H, then T and S are not conjugate. They are not conjugate, right? But in fact, one can show that they are not even spectrally isomorphic, not spectrally isomorphic. So the question is something which is spectrally isomorphic but not conjugate, for example, some simple cases. So one can define, say, two-dimensional torus k square to k square. Say, one can do like this. This is say Az, where A is what I have just now said, and sorry, ZPW. And you think of another operator, say S of ZW. Sorry, this one can define as AZ and ZQW. Right, where P and Q are integers. P and Q are non-zero integers, right? One can say that P and Q are non-zero. One. So we can look at these. So again, the entropy, if one is working out the entropy for capital T and S, then they are zero. And they are spectrally isomorphic. They are known to be spectrally isomorphic. But if we take both the integers P is not equal to Q. In fact, it should not be equal to, yeah, it should. So if P is not equal to Q, then not conjugate. So what I'm trying to say is this was a kind of study. So a lot of study have gone into this. So entropy, therefore, one cannot say that it's a, in this sense, it is an invariant which helps in distinguishing dynamical systems through through this aspect, but it's not a good invariant if one is looking at relation of conjugacy on the class of transformations with zero entropy, for example. So then one studies, say, for example, Bernoulli transformations and Kolmogorov transformations, and then Bernoulli transformations are, and relationship between Kolmogorov transformations. So one can see that Bernoulli transformations are Kolmogorov, but Kolmogorov are not Bernoulli, and then there are many interesting things which carries on this direction. So this is the way I just thought of telling you that this is how the theory of entropy began in ergodic theory. Let me go back to my slides. Yeah, I was here. Yeah. So the in 2065, Adler and they defined, I think it was in Transactions of the American Mathematical Society, the paper introduced the notion of topological entropy of a continuous self map of a compact metric space as an analog to measure theoretic this thing, entropy, which I just now thought of. So I would like to give you the how it is actually done here. So if you take two open covers and F is continuous self map, then one can define the join and the meet of this. So the join of alpha and beta is the open cover. This one. So n alpha denotes the number of sets in a finite subcover of alpha with smallest cardinality. That's a number we are associating. And the entropy of open cover, first of all, we define. So that is capital H alpha. And this is log of n. So we are motivated through that definition. And if you have a function f from x to x with respect to the open cover alpha, then the entropy little h, that is for the function f with respect to alpha, is this. And now we need to have a definition which is independent of alpha. So that's how it is. One talks about the topological entropy of a system is defined like this. So Bowen actually has given another definition. Bowen is actually Smale proved the decomposition theorem, and for up to topological transitive sets, and then Bowen did it for mixing sets, one of the famous theorems. So he was instrumental in defining, sorry for that question mark. So a finite set is n alpha separated for, so notion of separation comes into this, and SNF alpha the maximal cardinality of n alpha separated set. So yeah, it takes a bit of a time to digest this, but this is how it goes. And the topological entropy of F is also defined as this thing. So yeah, this is how the topological entropy is defined. Another entropy and important thing is notion of distributional chaos, which is based on asymptotic measure of the distance between two trajectories, the orbits. So Schweitzer has described how the theory of distributional chaos was motivated from the theory of probabilistic measure space. The notion of distributional chaos was initially defined for interval maps. It was a big question whether it goes for higher dimension or not. I'll comment on that. Later on, the notion was extended for compact metric spaces. So distributional chaos is considered as a very important generalization of Lee York chaos because it is equivalent to positive topological entropy. So that's how they are interlinked. And some other concepts of chaos when restricted to the compact interval case. So compact interval case, it gives you many other things, but the moment we go outside the domain, then it is the distributional chaos do not transfer to the higher dimensional case. So that is what I was trying to mention. Just for the sake of so if you look at continuous map on an interval close and bounded, of course, then F is distributionally chaotic of type 1, there's a type 2. So that is if and only if positive topological entropy. So topological entropy has played a very vital role in this determining the chaotic behavior on various topological spaces. Smithel is another profound researcher in this area, wherein a lot of recently, some couple of years back, his 75th birth was celebrated. The following result strengthens the result. This is important, which I have stated here, that this is what we can think of. If F has a regular shift invariant set, then it has an uncountably distributionally chaotic set in which each point is recurrent but is not almost periodic. So not almost periodic, therefore not periodic. But periodic sets, the density of periodic set, for example, is very important. For example, you just look at a tent map. Look at a tent map, for example, uh, on a closed interval and just tent map like that. 0 stays here and half goes to 1 and then 1 goes to 0. If you look at the dynamics of this tent map, then also it's very interesting. It has in dense set of periodic points, for example, and it has some equivalently other very distinct kind of other properties also. It is equivalent to a logistic map for a particular values of R, for example. So yeah, they have been explored in a very uh, extensive manner. So yeah, so yeah, so yeah, as I'm saying, the each part is recurrent but is not almost periodic. I think I'm done with the time, or I have some. How much time I have?
Yeah, another couple of minutes you can take.
It's okay. So I think I'll just say this: the continuous map of a compact metric space is P chaotic if it has pseudo-orbit tracing property and the set of all periodic points of F is dense in X. So the P chaotic map from a continuum to itself is Devane chaotic and exhibits distributional chaos with positive topological entropy. This is another very recent, this is very interesting results. This is, yeah. So another notion of strong chaos is stronger than Devane's definition of chaos or positive topological entropy is specification property. Let me give you a feel of what is specification property. We are deeply involved in the area in this specification property. One of my students has recently contributed some very good results he's published. The specification property for homeomorphism on a compact metric space has turned out to be an important notion in the study of dynamical systems. In what way? It was first introduced by Bowen, as I said, a distinguished mathematician, to give the distribution of periodic point for axiom A diffeomorphisms. What are the simple example of axiom A diffeomorphisms? Again, that 2 by 2 total automorphism you can think of. I just explained 2 by 2 matrix, you can take or 3 by 3 matrix and with the specific kind of integers which I said, determinant plus minus 1 and so on and so forth. So you can think of those total automorphisms. Those total automorphisms are simple good examples of axiom A diffeomorphism. They are C infinity. Yeah. Informally, what does the specification property tells you? It means that it is possible to shadow two distinct pieces of orbits. It's actually next to possible, like to trace an actual orbit. We all know we have to. So there is a natural notion of pseudo orbit. So you have a pseudo orbit that x. So you have a sequence, a bisequence. So x0 goes to you f of x0. It is in the delta neighborhood of x1. Then fx1. It is in the delta neighborhood of x2. So it's a small neighborhood. So each time you hit, it is in the delta neighborhood. So if such a thing happens, you say it's a delta pseudo orbit. And if there is an actual orbit which is epsilon close to that delta pseudo orbit, you say that it is epsilon traced. So this kind of tracing is available with all axiom A diffeomorphisms, total automorphisms. These are beautiful things like. So these notions, for example, this pseudo orbit tracing property. Now this has been studied extensively on the pointwise scale. And recently, the notion of error has been induced, which is this is a paper by Morales in Journal of Dynamical Systems, and another paper, a couple of series of papers which have come in this area. We have also contributed in this. So this is area where this is, and then the study of the topological stability there. So topological stability, Walter studied it like these are all topological stable homeomorphisms or diffeomorphisms. So uh, what happens if it is not globally topological stable, and how best we can claim that in piecewise manner we can have this. So yeah, so the specification plays a very important role. I'll close after this. Informally, the specification property means that it is possible to shadow two distinct pieces of orbits, so not the whole orbits, chunks of orbits, right, which are sufficiently apart in time by a single orbit. There's a single orbit, two distinct. Once it happens, so of course, very natural questions in it. This notion is extended for different types of spaces, right? You think of a phase. Yeah, so yeah, I wanted to get into expansivity and shadowing, but I think time is not going to permit me. So I'll stop here. If you have some quick questions, I can try to answer.
Thank you, Professor Das. So any questions or queries? Comments? So if there are no comments, let's thank the speaker.
Thank you.
Thank you, Professor Das.
Thank you.
Thank you, sir. So I thank both the chairperson and the speaker for their time and experience there with our participants. So thank you, Professor Suhakar, to you also, and Sir, Professor Tarandas.
Thank you.
My pleasure.
Both people accepted my request to be part of this conference.
Thank
and
you.
Sir especially has shared his knowledge and experience with our participants. So thank you once again, sir.
Thank you. Good luck.
Thank you.
Thank you.
Thank you. Thank you. Thank you. So next talk is scheduled to be of Professor John Parker from Durham University, and the title will be Geometry, Relations and Discrete Groups. And to chair his session, I invite my friend Professor Bankeshwar Tiwari from the HU Varanasi. Professor Tiwari, have you joined? Yes. So
Yeah.
over to you, sir.
Okay, thank you, Professor Gauri Shankarji. So I think the scheduled timing is 2:30. So can we wait for 3 more minutes.
Yes, we can wait, and in the meantime, you can introduce after 2 or 3 minutes.
Yeah, sure. Yeah, because the allotted timing is
60 minutes.
2:30, so it's not good idea to prepone the schedule because yeah.
Wait for 2-3 minutes and then introduce it.
Yeah. So good afternoon, Professor Parker. Yeah.
Good afternoon.
Good afternoon. And we are very much thankful to you that you have accepted our request to be part of this conference.
Well, thank you very much for the invitation. It's a great pleasure. Of course, I would like to be physically in India, but doing it over the internet is the next best thing.
Yes. So let us wait for 2-3 minutes.
Yeah.
Can I just check that my slides will share?
Yes, of course. Yeah.
Yes, of course.
Good idea. Yeah. We can utilize this time for checking the slides.
Okay. Hang on. That's just a moment. This is. I have my iPad connected. I have my iPad connected on a cable. So if it just says I can share my entire screen. So should I try to join using a second device then? Because I would really prefer to be able to write on my screen. Okay, let me try this again. What's happening? Nothing is happening here. Okay, so I don't want to do that. I want to.
Yes, it is fine.
I was hoping I would be able to. Okay. So now I can't see you. What's happening here? I don't want to do that. I want to. Okay. Let me stop sharing that.
I think you just open your document. You open your document. You go on your document. I think it will be
yeah. But I would like to do it on my other device. So perhaps I need to just join in 2 different ways. So just give me 1 second. So what is this? What is the, whoops, lost it now.
So I think it's already 2:30. So I think.
Okay.
Yes.
In the meantime, you can.
I'm trying to join on my second device. So can you just give me?
Okay.
You have to close the wires of one device.
Just a moment. Something very strange is happening. Okay, fine. This is not working, so I will. Okay. Right, I will try again. Okay. Okay, can you see that now?
No, no. It is not shared, in fact. So please share your slides. Yeah.
Can you see my slides?
Yeah,
Yes.
yeah. Okay.
Okay, good.
Okay,
Right.
okay. So, yeah. So let me introduce Professor Parker. So good afternoon, all the participants. So it's my pleasure, indeed honor, to introduce Professor John R. Parker. He's Professor of Geometry, Department of Mathematical Sciences from Durham University, Durham, UK. And his main area of research is hyperbolic geometry, discrete group fraction on it. And today he will speak on geometry, tessellation, and discrete groups. So now I request Professor Parker to please start to talk. Over to you, sir.
Okay, well, thank you very much indeed for the invitation. It's a great pleasure to be here and to speak to you. And apologies for my technical error. I'm used to sharing things in Zoom. I'm not so used to sharing them in the Google setup. So I was asked to give a general talk on my research area, which I have done, but also this is a conference about new developments. So perhaps the last two slides, I will give you a little bit of a hint about some of the new developments in this area by myself and other people. So let's begin. Here's a set of ideas. As people studying geometry, we want to study the geometry on a manifold M. But that can often be very hard, particularly if you're in high dimensions, if you're trying to visualize what is happening on a manifold. So to get around this, there are various techniques that have been evolved over the years by different people using groups. And really, my research is about the interaction between geometry and groups. So here's a formal definition for those people who we want to think of that as being like a copy of this manifold X, and we want the transition functions to be in G. So in what follows, I'm going to work through two very simple examples. The first one is something that hopefully everybody is familiar with, and that is a torus where we would have X as being the Euclidean plane, and we would have G as a group of translations of the Euclidean plane, and we would take the quotient to find the torus. And then I'm going to do a similar, by analogy, I'm going to do this in the higher genus surface case for a surface of genus 2. But the ideas that I'm going to present these are just two very simple examples in a much more complicated setting. So the upshot of all of this is it gives me a representation of the fundamental group of my manifold into this group G, and the image should be discrete. So discreteness is one of the things in the title of my talk. And if this image is discrete, then we can identify the equivalence classes of this action, and we can write M as a quotient. So now what I've done is I've taken my manifold M, which is hard to study, and I've taken a space X where I can probably do things much more easily, and I've written M as a quotient by the action of a group of isometries. So let's go to the first example. This is something we're probably very familiar with. It's probably the first example in topology that we would talk about covers and universal covers. So if I start out with a torus, I can cut it along this sort of purple curve and the blue curve, which I'm calling A and B. First of all, if I cut along A, I'm going to get a cylinder. And then if I cut along B, I'm going to get a square or a parallelogram. And the little green circle now around the vertex has been broken into 4 different arcs. So if I wanted to reassemble my torus from this square, all I would do is I would glue together the opposite sides and I would obtain the torus again. Now, instead of doing that, let's take a second copy of this square and then glue together along the sides that would have been glued in my original case. So in my original torus, I would glue the left-hand side to the right-hand side. Now I take 2 copies and I glue the right-hand side of one to the left-hand side of another, and then I get 2 copies sitting together according to the same recipe that I had to do my original sides. So that gives me a double square. Now I continue to do this, and maybe I put a copy of using the B curves. Now I get 3 copies there. And now I glue another 4th copy in, and something magical happens at this point because I'm gluing both along the bottom of this square and on the right-hand side of this, and everything all nicely fits together around this vertex. And the reason why this all works is that the internal angles of my square, because I have 1 copy of the bottom left, the bottom right, the top right, and the top left, they all add up to 2 pi. And so everything can be glued together beautifully, smoothly at that point. So if I keep on doing this, I get a copy of the Euclidean plane with a grid, and the little green circles that I had before, which were broken up when I took my square, have all been joined together beautifully to get back to circles. So let's summarize what I've just done. The union of all of those squares forms the universal cover of the torus. So that's the simply connected covering space. And in that case, it carries a copy of the Euclidean metric. Behind the scenes here, the fact that the torus has genus 0 means that it naturally is Euclidean by the uniformization theorem, and the Gauss-Bonnet theorem gives me the curvature, either from the Euler characteristic or from the angle sum of the square. And now, in this copy here, each of those squares is an image of the original square by a translation. And each of those translations preserves the metric that I have on E2. And so therefore they're a Euclidean isometry. And if I let gamma denote the group of all of the translations, so perhaps if that was my original square with the arrows here, then I have lots of translations to the right, upwards, downwards, to the left, and some sort of random other combinations of those. So that would be the group gamma, so that every one of those squares is the gamma image of my original one, and in a unique way. And so then I can write my torus as the quotient of the Euclidean plane by this group of translations. And really what's going on here, in order for that quotient to make sense, the group gamma needs to act properly discontinuously. What does properly discontinuously mean? It means that for any compact subset of E or E2, then the set of all elements of my group, so that the image of my compact set under the element of the group still intersects my compact set, the number of all of those elements is finite. So obviously if I took a little tiny compact set inside my square, the only copy of the group, the only element of the group that would map this set onto something that intersects itself would be the identity. But if I take a huge disk, then I would have to think of all of the copies of the square that intersect that disk. Okay, and in order for this group to act properly discontinuously, that means that it needs to be discrete. So it naturally carries the discrete topology. It's a topological group, and the group of isometries is a topological group. And as a subgroup, that topology restricts to the discrete topology, which means that any sequence of elements that converges within this topology, that has to eventually be constant. So that means that the images are nicely separated out. And so if a group is properly discontinuous, it has to be discrete. And if a group is discrete, then for suitable actions, then it will be properly discontinuous, but there are other actions where it may not be. Okay, so let's see how this helps us with our geometry. So we have I've drawn a picture of a curve on my torus, which somehow winds lots of times around. And maybe I want to study the geometry of that curve. Perhaps I've pulled it tight to form a geodesic. Well, if I cut my torus open, I get a bunch of strands, which are joining the different sides of my torus. And if I then just write one copy of this on my universal cover, that turns into a nice straight line. And so I can do lots of interesting geometry. So perhaps I want to think about the number of times curves intersect, for example, which would be a little bit hard if I'm just working locally on the torus. But if I lift up to the universal cover, it becomes a much easier problem. Now, this talk is supposed to also be a general thing and have a little bit of entertainment value. So here is a totally gratuitous picture of a piece of art, which I found on the internet. Some sculptor called Peter Coffin made a thing that looks like a curve on a torus, which would be the handle of this spiral staircase. So that's just a piece of gratuitous things for your entertainment. So now let's try to run through this structure that I've just performed. Let's try to do this in higher genus. So here's a copy of a picture of a curve of genus 2, and I've done the same trick of namely taking a generating set for the fundamental group. That was what was going on behind the scenes before, which, as we all know, if we have a base point here, if you can see my cursor, at the intersection of all those curves, then I have a loop for various different generators of the fundamental group. And now, what happens if I cut along all of those? Well, I get an octagon. And this is the standard way of decomposing a surface into a fundamental domain. Now, if I were to take a little neighborhood of this base point where all of the curves intersect, then on the original torus, the internal, all the angles there would have to add up to 2 pi. But if I were to try to do this using Euclidean geometry, then the internal angles of this octagon would have to add up to 6 pi. And so something's going wrong. I would get a singularity if I tried to glue everything together. And so that forces me to not use Euclidean geometry, but to use hyperbolic geometry. And that's the sort of where my interest in hyperbolic geometry comes in, because I want to study surfaces or higher dimensional analogs of surfaces, and often hyperbolic things are the place to go. So if I can now draw a tessellation, but I can do this in the Poincare disk model of the hyperbolic plane. And so you can see that the basic octagon now is colored in this sort of beigey color. And then there are other copies where you can see the letters A, B, C, D, etc. And they hyperbolically, those look identical to the beigey color octagon, but to our Euclidean eyes, they look slightly different. And moreover, that there are 8 copies of those all meeting together around one of the vertices, and the internal angles all nicely add up to 2 pi, and I get a beautiful tessellation. So I stole this image from a paper by Bill Goldman, who used to be my postdoc supervisor many, many years ago. And so it's a nice picture. So let's repeat my discussion of what that I had for my torus, but to see what's changed now. So the union of all of the octagons forms the universal cover of my surface. But now, instead of the Euclidean structure, it carries a hyperbolic structure. So I'm calling this H2R. And behind the scenes, the thing that's going on is the Gauss-Bonnet theorem, again, giving me the curvature from the Euler characteristic of the surface, all from the angle sum of that should be octagon now, apologies. And then each of the octagons in this tessellation is the image of the original one by some hyperbolic isometry, and let gamma denote the group of those isometries. And that means I can write my surface of genus 2 by a copy of the hyperbolic plane by this group of isometries. And again, in order for this quotient to make sense, the group needs to act properly discontinuously. I've reminded you what that means there. And for that to happen, gamma needs to be discrete. So that's the sort of the circle of ideas that underlies most of the research that I do. So we can get lots of other tessellations of the Poincare disk. I've got one by squares there, another one by pentagons, a nice picture by Escher of these sort of things that I think are probably birds, but they may be fish, I'm not quite sure. And then another one with Poincare himself tessellating the Poincare disk. Again, this is a little piece of nice entertainment. These pictures I stole from the internet. So what's the main idea behind this? In order to run all of those arguments, I need to find a discrete group of isometries of a simply connected metric space X. And so this is going to be my GX structure. So G is going to be a group acting on X, and gamma is going to be a discrete subgroup of G. So in that example, X was the Euclidean or the hyperbolic plane, but we can work in higher dimensions and greater generality. So here is a big question. Suppose we're given a group of isometries of a space X. How can we tell whether that group is discrete? So if we can tell that the group is discrete, I can find a quotient, and then I get a manifold or an orbifold, and I can study geometry there, and lots of things work beautifully. Almost the same question of this is, how can I tell whether that group acts properly discontinuously on X? As I said, in order for it to act properly discontinuously, the group needs to be discrete, but there are some bad actions where a discrete group could act non-properly discontinuously. But for the purpose of today, we can think of those two things as being the same. So there are methods to show that gamma is not discrete. So if somebody walks up to you in the street and hands you a group and says, I'll kill you if you don't tell me whether this is discrete or not, what could you do to show that it was not discrete? But I'm not going to talk about those things today. There's lots of beautiful maths in there, but I want to focus today on two methods where I can show that the group is discrete. So I guess I should say at this point, are there any questions? I seem to be going through the material reasonably fast, so I probably need to slow down. So it probably means that I've lost half the audience. So please ask if there's any questions. Okay, well, I'm assuming that silence means that you're... Okay, so the first method is via polyhedra, and this is the Poincaré polyhedron theorem. I should say a lot of these ideas for the rest of the talk, I'm giving some talks in Pune, and I've given a whole talk on the second topic, which will be arithmetic groups, and I'm about to, in a couple of weeks' time, give a whole talk on the Poincaré polyhedron theorem. So all I'm going to do today is I'm going to focus on some of the general ideas. If you want to see more details, you can watch the video or attend the talks in Pune. Okay, so if we're given a group of isometries, we want to find such a polyhedron whose gamma images tessellate X. So that would be like the squares in the picture of the torus, or the octagons for the hyperbolic plane. Alternatively, if somebody gives you a polyhedron, and all the way back, we had this idea of this square and ways of attaching the sides together. That will be on my next slide. So if we're given that polyhedron, that square, and a way of attaching the sides together, then the device to show that all of this works is called the Poincaré polyhedron theorem. So Poincaré proved this for the hyperbolic plane and for hyperbolic 3 space, and then the ideas have been generalized to quite many different ways. This is quite a delicate theorem to state. There's as I will be telling in my other talk, there was a paper published probably a bit over 20 years ago, giving counterexamples to every known statement of the Poincaré polyhedron theorem apart from one, because people had not stated it correctly. So it's a very delicate theorem to state. In practice, it's quite easy to use, and it's very powerful. So not only does it give me the fact that this group is discrete, it also gives me a presentation for the group in terms of generators and relations. It enables me to calculate the stabilizer of the facets of the polyhedron, so the sides, the vertices, the edges, and so forth. I can use these stabilizer groups to calculate the orbifold Euler characteristic. So maybe just the ordinary Euler characteristic. If I have a manifold, sometimes we have some special sorts of singularities where the quotient becomes an orbifold, in which case I would have the orbifold Euler characteristic. And there are many cases where I can use the Gauss-Bonnet theorem to use the Euler characteristic to calculate volumes. And then this can be very interesting, and there's many important things where this happens. Basically, in most cases where the manifold is even dimensional. Of course, in odd dimensions, the Euler characteristic is 0, so that's not very helpful. Okay, so let's go through this tiny bit more slowly. So the input of this theorem is a polyhedron, P, together with a set of side pairings. So that's a way of gluing sides together by bijections, like the opposite sides of my square. They must satisfy a set of conditions to make sure that the polyhedron fits, different copies of them fit together well with the image under the different side pairings. And so these are codimension 1 facets, the sides. And then I have codimension 2 facets, which are generally called ridges. And then I have some cycle conditions around ridges that ensure the images of the polyhedron fit together well around each of those ridges. And there are some further technical conditions that ensure the union of the images covers the entire universal cover. And notice one of the great things about this theorem is it only has codimension 1 and codimension 2 conditions. So for polygons, and that's really the case I'm dealing with today, that's not very surprising because I only have codimension 1 and codimension 2 facets. But when I'm in higher dimensions, all I need to do is codimension 1 and codimension 2. And that's incredibly useful because it the conditions would get increasingly difficult to check if I had to go all of the way down. So here are the conditions. I'm not giving you the precise details, just giving you the general flavor of them. And if I'm satisfied these conditions, then the group generated by the side pairings, that has to be discrete. And then a complete set of relations for this group gamma would be given by some reflection relations, which is when if a side is paired to itself, and cycle relations, which come from the way that the things go around the vertices. So let's see how this works in our favorite example of the torus, the simplest example we could probably think about. So the input here is a square, and I would have translations TA pairing the left-hand side and the right-hand side, and TB pairing the top and the bottom. And I would also have their inverses, so the top gets paired to the bottom and the right-hand side to the left-hand side. And so now I can fit a copy of my square together with a copy under the translation, the left translation, the one that moves to the right, called by TA. And similarly, I can fit together TA inverse, TB, and TB inverse, just like we saw when we were talking earlier on. This is really formalizing this process that we had earlier. And then if I fit around a vertex, then I'm going to get, I told you there was this cycle relation, which is this one, which says, let me see, if I start off in this top right-hand square, and I go first do T, because of course I have to read from right to left because I'm acting on the left. So I first do TB inverse, that takes me down to the bottom right square, then TA inverse takes me back to the bottom left square, TB sends me upwards to the top left, and TA sends me back up to the top right. And then that means that's like going around this little green circle. And that should take me back to the identity, and that gives me a relation in the group, which is the commutator of TA and TB. And that tells me that TA and TB should commute with one another. So let's see why some extra conditions involving completeness are needed. I'm just going to focus on one particular example. Suppose that I had a strip. So this is this blue strip between 1 and 2 in the hyperbolic plane. And suppose that I have an isometry that glues the left-hand side to the right-hand side. Now, there's an obvious isometry which would just be translation by 1. So Z goes to Z plus 1. But let's just suppose I do it in a different way. I'm going to use Z goes to 2Z. And so you can see these dotted lines here. So what's going to happen is this point at 1i is going to go to 2 plus 2i, and the one 1 plus 2i is going to go to 2 plus 4i, and so forth. So now let's see what happens if I take images of the, and of course I can embed this into more complicated examples. This is just a simple example. So what happens if I look at all of the images of this under powers of A? Well, the image under A of the strip is the strip between 2 and 4, the next one between 4 and 8, and so forth, going positive powers. If I go negative powers, I'm going to get the strip between 1/2 and 1, between 1/4 and 1/2, between 1/8 and 1/4, and these all pile up on the imaginary axis. So in particular, the strip A to the power K of S is the strip between where the real part of Z lies between 2 to the K and 2 to the K plus 1. And of course, taking K negative, then this all piles up at the real part of Z is 0. So the images of this strip do not cover the whole of the hyperbolic plane. And so this is a problem, and because I wanted to have a tessellation of the whole space. And this is why there are similar other problems that arise, but this is why completeness is an issue. So that's the Poincare polyhedron theorem. To summarize, we have a polyhedron with some ways of gluing pairs of sides. We have some conditions that say that the sides need to fit together nicely, and also around the codimension 2 facets, which are the ridges. And then there's some extra technical conditions, such as this one. In this case, the technical condition would be that if I have 2 sides that meet in an ideal vertex, in this case infinity, then the side pairing here would have to preserve horospheres or horoballs, or in this case horocycles, around that point. So I would only be allowed translations in this case. Okay, so the second way of showing discreteness is using number theory. So the simplest example of a discrete subgroup of a continuous group is the integers contained in the real line. Now, we've known about this for most of our lives. So there's a picture of a ruler. I mean, we learnt in probably early childhood that you can measure distances, real distances. You can use them by the inches or the centimeters on your ruler, and those are nice discrete things and then you can always sort of move things around. So, and you can take, if I have a length that isn't a whole integer, I can take off the integer part, and it always comes back to my nice little interval between 0 and 1. So a group is called arithmetic if the discreteness is a consequence of the discreteness of the integers in the reals. There's a very complicated technical definition. I won't describe that, but I just want to give a very simple example. And that is the modular group PSL2Z. So that is the group of Möbius transformations acting on the upper half plane, AZ plus B over CZ plus D, where AD minus BC is equal to 1, and ABCD are all integers. Now, here's a picture of the action of this on the upper half plane, and the gray shaded area is a fundamental domain. When I was first a graduate student, I was reading, there's a beautiful book by Magnus called something about tessellations and discrete groups. And the purpose of that book is to describe some of the pictures in the famous book by Fricker and Klein. And he has a beautiful picture of, they're beautiful hand-drawn pictures from the 1890s. And there's a beautiful picture of this tessellation. And Magnus just gives me the definition here. And he said, of course, it's obvious that this group is discrete. Now, when I was a first graduate student, well, I knew about this tessellation, and I knew about the fundamental domain, and I knew that if I glued together the left-hand side to the right-hand side, and the left-hand arc of the unit circle to the right-hand arc, then I could show that that was a fundamental domain, and therefore the group acted properly discontinuously, and therefore it was discrete. And I sort of knew that chain of argument, but it did not seem to me to be obvious. And what I had totally missed in my young naivety was the fact that if I take a sequence of Möbius transformations like this that converges, then that's equivalent to the matrix entries, or Möbius entries converging. They're all integers, and so any convergent sequence of integers has to be eventually constant, and so this sequence has to be constant. And so that's really what's going on with these examples. We're not using the geometry, we're using the discreteness rather than the proper discontinuity. And it's all to do with the fact that the integers are discrete in the real line. Okay, so if a group is discrete, because of this, it's called arithmetic. And there's a connection between what are called lattices and arithmetic groups. So let's just, a lattice, so in all of the examples I had before, where I have my manifold as X quotiented out by gamma, gamma is called a lattice if M has finite volume. If M is compact, the lattice is called uniform. If it's not compact but still has finite volume, it's called non-uniform. Okay, so that's just a technical definition which we'll need for this slide. Now, suppose that X, so this is where I said we're getting towards some more technical things. So there's a lot of words on this slide, and if you don't understand the words, just kind of feel the ideas. So I'm going to just restrict myself to the case where X is a symmetric space associated to an irreducible Lie group G of non-compact type. So the simplest example you should think of is the hyperbolic plane associated to the Lie group PSL2R. Okay, so if I'm in this context, all arithmetic subgroups of G, this G here, they're lattices. So that's a big result of Burrell and Harish-Chandra. All arithmetic subgroups are lattices. Conversely, all lattices in G are arithmetic, so that's going the opposite way, under many conditions, many times. So first, when the rank of this group is greater than 1, so the rank is the dimension of the largest Euclidean space that I can isometrically and totally geodesically embed in M, or the largest flat in the terminology. So in that case, Margulis superrigidity tells me that all lattices in G are arithmetic. So that just leaves us with 4 families of groups. And in the last 2 of those families, the same thing is true, that X, the space X, is either a quaternionic hyperbolic n space or the octonionic hyperbolic plane. All lattices are arithmetic in those cases as well. That was shown by Corlett and by Gromov and Shane. So we almost have a bijection here. All arithmetic groups are lattices, all lattices are arithmetic. So perhaps if that were true, then we wouldn't need to study geometry. We could go off and study manifolds using number theory, but we're left with some interesting cases. And these are the cases that I spend most of my life thinking about. The first case is where X is real hyperbolic n space, or ordinary hyperbolic n space, and G is the group SON1 up to commensurability. So commensurability, the natural invariant that is associated to arithmeticity. So 2 groups are commensurable if their index has, so if their intersection has finite index in both of them, and I'm also allowed to conjugate one of them around. So this is the natural thing. So for example, for SO21, that is commensurable to PSL2R. And the second case is where X is complex hyperbolic n space, and this group G is SUN1. So SON1 are matrices with unit determinant preserving a quadratic form of signature n, 1, n positive eigenvalues, 1 negative eigenvalue. And SUN1 is the same thing except with a Hermitian form. So it's a natural complex analog of SON1. Okay, and the lattice is called non-arithmetic if it is not arithmetic. If it's still a lattice but does not satisfy this technical condition that we were using up at the top. So there are examples of non-arithmetic lattices in SON1 for all values of n. That's due to Gromov and Pitetsky-Shapiro. There were examples known in lower dimensions before that, but theirs was the first construction in all dimensions. There exists non-arithmetic lattices in SU21. That's the result of Mostow in 1980. And there exists an example of a non-arithmetic lattice in SU31. That's Deline and Mostow in 86. So a big open problem is it's not known whether there are whether there are non-arithmetic lattices in SUN1 for n bigger than or equal to 4. So I've taken you from very simple ideas through to a big open problem. And that's been described as one of the biggest problems in discrete subgroups of Lie groups that's still open. So I want to focus a little bit in this, this last case to just tell you that there's very few examples known. So let's focus about the number of known examples of non-arithmetic lattices up to commensurability. So in the case where n is equal to 1, that is SU11, that's the same as SL2R or SO21, then there's an countably infinite number of non-arithmetic triangle groups. This is due to Takeuchi. I talked about Takeuchi's results in Pune like last week or the week before. But actually, there's a cheaper way to get examples here. In this case, we have continuous deformations of all lattice groups, surface groups, and so surface groups, sorry, and so therefore I would have uncountably many non-arithmetic surface groups. So that's a very cheap way to get examples. So somehow that's reasonably well understood. For SU21, in this paper of 1980, Mosto constructed 7 examples. This is quite a phenomenal paper. It's 100 pages long. It's an early example of using computers to verify some very technical results. He needs to develop a huge amount of theory, which he does. It's a magnificent paper, magnum opus. The following year, Livney gave another example. I guess he didn't really talk about its arithmetic nature, but it is a second example. He was using a completely different method altogether, which I won't have time to go into. Then Deline and Mosto, they came and they wanted to unify the ideas from the previous papers and see if they could find some extra example, and they found one more example. And that's basically where the situation stood for quite a long time. And then a few years ago, about 5 years ago now, Martin Dereau, Julien Popper, and myself, we found 13 more examples. Actually, the paper with those examples was published this year. The first new examples were published 5 years ago. And so these 22 examples, those are the only known examples of non-arithmetic lattices in SU21. The situation is even more sparse in SU31. In the same paper of 1986, Deline and Mosto found one new example in SU31, and for many, many years, that was the only known example. Martin Dereau has recently constructed one more example, and those are the only 2 examples that are known in SUN1. And so that's all. Thank you for your attention. Are there any questions?
So thank you very much, Professor Parker, for this excellent talk, starting from basic tessellation and to this symmetry of this in fact, rich symmetry of this hyperbolic geometry. So thank you very much. So is there any question or any comment from audience? I can see Dr. Nalini. Would you like to ask anything? Dr. Nalini Ramalata. You have raised your hand. Do you have any question? Or any comment from any participant? So I think there is no comment or question. So I think your email is already there. If anybody has any question or query to learn about this rich symmetry of hyperbolic geometry, you can directly contact Professor Parker. So thank you very much, Professor Parker, for your excellent overview of this hyperbolic geometry and its symmetry.
So thank you very much. It was a great pleasure, and I hope the rest of the conference goes very well. Thank you.
Yeah. Okay. Thank you.
Thank you, Professor Parker.
You're very
It is
welcome.
a pleasure and honor to host you, and I am very much thankful to you that you accepted our invitation and gave a very excellent talk on this topic.
Okay, thank you.
And
Okay.
once again, I am very much thankful to my colleague, Professor Tiwari ji, that on his short notice, he accepted my request to chair this session.
Yeah, in fact, this was a responsibility of Professor Krishnendu, but yeah, there was some.
He informed that he is traveling somewhere, so
okay,
he could
yeah.
not join.
Okay, thank you.
So
Thank
now we will have a 15-minute break, and next session will start at 3:30, and there will be paper presentation by participants.
Okay. Okay, thank you, Professor Parker.
Okay, bye.
Hello, hello. I'm audible. Hello.
Yes, sir.
Okay. So, good up. Hello.
No.
Hi, yes, sir. Okay.
Okay.
ठीक है sir.
So
Uh,
start.
okay, sir. So, good afternoon to all. And this session is chaired by me. And dear all participants, before start the session, I inform all of you that there are the 9 paper presentations in this session, and for each presentation we have only the 8 minutes. So I request all the participants to complete your presentation within 7 minutes, and 1 minute will be given for the question answers. So we can start on this session. So our first participant, Buddhadev Pal and Santosh Kumar from Banaras Hindu University, Varanasi, and their paper presentation title is K-type slant helix on space-like and time-like surfaces. So, Buddhadev Pal, you can share your screen and start your presentation. Santosh?
Yes, sir.
Okay, you can start.
Am I audible, sir?
Yes, sir.
Good afternoon, everyone. My name is Santosh Kumar, and I am a research scholar in the Department of Mathematics, Banaras Hindu University. My topic for today's presentation is K-type slant helices on space-like and time-like surfaces. These are my outlines for the talk. First, introduction, preliminary. Then we will define K-type slant helices and some theorem. And after that, one example also given. And we will also find the method to generate first axis for K-type space-like Darboux helix on space-like and time-like surfaces. And finally, references. Introduction. A curve gamma in Euclidean space whose tangent vector makes constant angle with some fixed direction is known as a general helix. This condition was first stated by M. L. Lansrate in 1802 and proved by B. de Saint-Venant in 1845 and further revisited by the M. Boris in 1998. Slant helices are the generalized version of general helices we find we find a fixed direction whose inner product with the which makes a constant angle with the normal of a curve gamma, and the necessary and sufficient condition for any arbitrary curve gamma to be a slant helix, the function defined in this way must be a constant. ATLE and L. Raphael in 2011 introduced the slant helix in Minkowski space. Unit space curve gamma in three-dimensional Minkowski space is said to be a slant helix if there exists some fixed direction vector u whose inner product with principal normal is constant, where n is the principal normal of gamma. The curve in Minkowski space may be space-like, time-like, or light-like. According to these causal character of the curve, we get the necessary and sufficient condition for curve to become slant helix. Like, for example, a unit speed time-like curve in Minkowski space be a slant helix if and only if one of the following two function is a constant. These conditions for unit speed space-like curve with space-like normal to become a slant helix is same as the condition defined for time-like curve. What if the normal of a space-like curve is time-like? Then we just focus on a one function ks. This must be constant. Whereas all the space-like curve with light-like normal are slant helices, and Darboux helices are those curves in which Darboux vector of the curve makes a constant angle with some fixed direction. These are my preliminaries. Now, a three-dimensional Minkowski space is a real vector space in which we define the scalar product in this way. Scalar product of xy must be minus x1 y1 plus x2 y2 plus x3 y3. Let gamma s be a some unit speed curve in Minkowski space, then the curve is said to be space-like if scalar product of a tangent vector field along curve gamma is positive, and its curve is known as the light-like if the scalar product is negative, and it would be called as a light-like if a scalar product is equal to 0. A surface in Minkowski space is said to be a space-like surface if unit surface normal is a time-like vector, and surface is said to be a time-like surface if the unit surface normal is a space-like vector. If T and B is the Frenet frame along any curve gamma s, then the derivative of T, N, and B defined by the equation 3.1. Condition for this is that the normal of the curve must be non-zero. If the normal of a curve is equal to a null vector, in that particular case, derivative of tangent normal and binormal will satisfy the equation 3.2. We know that now the box frame, as we know that the tangent vector field gamma dash s along the curve gamma lying on a surface M is also a tangent vector to the given surface M at that particular point. If Z is the unit surface normal at point gamma s on surface M, then we can construct a new vector by the rotation of a tangent and normal of the surface, which is written as y is equal to plus minus t cross z. Here plus minus sign is going to depend upon the whether the normal is a space like or whether it is a time like vector. For example, if space is a space like, it means z is a time like vector, so y must be a space like vector, so it must be y is equal to t cross z. This vector t, y, and z from another moving frame along the curve of the gamma known as the Darboux frame. Now we get new frame T, Y, and Z at each point, and other frame is Frenet frame, tangent normal and binormal, and the relation between these frame is given by the equation 3.3. And the derivative of a new frame tangent Darboux frame is T by dash, T dash by dash, and Z dash in terms of Darboux frame is given by the equation 3.4. The relation between Darboux frame and Frenet frame for a space-like curve with time-like normal on the space-like surface is given by equation 3.5, and the equation 3.6 for this particular curve gives the derivative of Darboux frame in terms of Darboux frame. Here we discuss the cases for a time-like surfaces. What will happen if the curve is a space-like and with space-like normal lying on a time-like surface? These are the relations. And now in this section, we will define to a K-type space like slant helix, and we will define the necessary and sufficient condition for a curve to become a K-type slant helix in terms of a geodesic curvature, normal curvature, and geodesic torsion. A space like curve gamma s on space like time like surface is said to be a K-type space like slant helix if there exists a known fixed direction vector u such that scalar product of a vk comma u is equal to constant, where a vk any of the Darboux frame field, like it may be tangent, it may be a bi, or it may be normal z, where c is some real constant. But if normal for K-type space like slant helix is 0, then it is also known as a K-type pseudo-null slant helix. Theorem 1. This theorem gives us the necessary and sufficient condition for any arbitrary curve gamma s, which is lying on a space like surface, will be a one-type slant helix if and only if it satisfies this equation. Condition is here: normal curvature, geodesic curvatures, and geodesic torsion, all of them must be a non-zero. And the x is for a one-type slant helix on a space-like surface is given by equation 4.2. We can see here, if we take the scalar product of u with t, we get some constant. If we take the scalar product of u with by, we get this values minus c, this long expression. If kappa g, tau g, kappa, and all these are a constant, then this expression is also become a constant. But if these are not constant, then this expression is not constant. So we give this conclusion from corollary 1. It's clear that every one-type space like slant helix with space like normal whose axis is not orthogonal to t with non-zero non-constant curvature, kappa g, kappa, and tau g are neither two-type nor three-type space like slant helix with space like normal. If gamma be a space like curve with space like normal on its surface M, then gamma be a one-type space like slant helix whose axis is orthogonal to t if and only if it satisfies the relation 4.3, and axis for a one-type slant helix with orthogonal to t is given by the equation 4.4. Here we define a space like a curve space like curve is space like normal, but whose geodesic torsion is a 0. In that particular case, curve will be a one type slant helix if and only if this satisfies the given relation. And the axis for a one type slant helix whose geodesic torsion is equal to 0 is given by the equation 4.5. And we made from above corollary some conclusion that every one type space like slant helices with space like normal and non-zero curvatures and torsion lying on the space like surface are neither two type nor three type slant helices. In notes, we discuss the space like curve with time like principal normal on time like surfaces. These results are not much differ as we have done for the space like curve with space like normal on a space like surface. So I just concluded them inside the notes. Here, theorem 7 is dedicated to provide the necessary and sufficient condition for any curve gamma S to become a two-type slant helix. And the axis for a two-type slant helix is given by 4.6. These axes are not orthogonal to T. It means U comma T is some constant which is not equal to 0. And this theorem dedicated to say that gamma be a space like curve with space like normal on the space like surface, then gamma be two type slant helix x is orthogonal to y if and only if it satisfy this relation. And these are some theorem corollaries, and this is for a theorem 11. If gamma be a space like curve with space like normal and zero geodesic torsion lying on surface M, then gamma be a two type space like slant helix if and only if the ratio of curvature function normal curvature and geodesic torsion is a constant. In corollary 12, if gamma be a two type space like helix with space like normal and zero geodesic torsion lying on some surface.
Hello, Santosh.
Yes, sir.
Please conclude your presentation within 1 minute.
Okay, sir.
You have
Then
taken
gamma
with
is
the 12 minutes.
Okay, sir. Okay. One type and three type is slant helix. Theorem 14, we provide the necessary and sufficient condition for a curve gamma S be a three type slant helix, and this is the axis of a three type slant helix. And these are results for to a space like curve with time like normal on a time like a surface. This is our example. M is a space like surface and gamma S is a space like curve with space like normal. These are how they look inside to a Euclidean space. Here the box B constructed the box vector A. Let gamma be a k-type space like slant helix with non-null normal lying on space like surface if there exists a constant direction v not collinear to axis of a slant helix, then that particular slant helix is known as a Darboux helix. These are our axes, f value of f, g and h, and these are references. Thank you.
Okay, so if anybody wants to ask the questions, you can ask. Hello. Okay, so I'm inviting the next participant, Sachin Kumar Srivastava, Merika Dhiman, and Anuj Kumar, Central University of Himachal Pradesh, and their paper presentation title is A Note on PR Semi-Slant Sum Manifolds of Parakemetsu Manifold. So, the Merika Dhiman, you can start your presentation. Hello.
Yes, sir.
So you can share your screen and start your presentation.
I will do.
And please remember your time. You have only the 7 minutes and 1 minute will be given for the question answers. Okay.
So is my screen visible?
Yes, screen is visible.
Okay. Good afternoon. My name is Merika Dhiman, a research scholar from Srinivasa Ramanujan Department of Mathematics, Central University of Himachal Pradesh. My topic of presentation is a study on PR semi-slants and manifold in Parakemetsu manifold. This is the outline of my presentation, which includes the introduction, preliminaries, which includes the basic definition of manifold and submanifolds. Third is the slant submanifold definition, and fourth PR semi-slant submanifold, and then references. The story of slant submanifolds as a generalization of the complex and totally real classes of submanifolds began by the author named Yu Chen for almost Hermitian and Kähler manifolds. He defined the slant submanifolds as the submanifold for which the Rittinger angles means the angle of phi x with its tangent space is constant for any vector field x. This angle, particularly 0 or pi by 2, leads to a complex or totally real submanifold respectively. For the case of pseudo-Riemann metric, the slant submanifolds were firstly studied by B.Y. Chen with two more authors for Lorentzian space forms. Then after P. Allegri carried out the same for Lorentzian Sasakian and para-Sasakian manifolds. Same author later studied the slant submanifold for para-Hermitian manifolds with more generalized definition on the basis of which we also defined slant submanifold for our N-bit space. First is the definition of almost paracontact metric manifolds. A 2m plus 1 dimensional smooth manifold M bar admits phi xi eta z structure with phi as a 1-1 tensor field, xi as a characteristic vector field, eta as a globally differential one form, and g as a pseudo-Riemannian metric is named as an almost paracontact pseudo-Riemannian manifold which satisfies these two equations. Where I represents an identity transformation of tangent space of M bar, a structure compatible pseudo-Riemannian metric G relates to eta by equation 3. Now the definition of para-Kenmotsu manifold. A paracontact pseudo-Riemannian metric manifold is called para-Kenmotsu manifold if it satisfies the given equation. For xy belongs to gamma T M per bar, where del nabla bar is Levi-Civita connection on M bar. On para-Kenmotsu pseudo-Riemannian manifold M bar, the following relation holds for x belonging to gamma Tm bar. Now the submanifold, let M be an isometrically immersed submanifold of para-Kenmotsu manifold M bar. Let us denote gamma Tm for the set of all tangent vector fields, gamma Tm per for the set of all normal vector fields of M. Then the Gauss and Wien-Cartan formulas are given as these two equations. For any zeta belongs to gamma Tm per and x y belongs to gamma Tm, where a zeta be a shape operator and h be a second fundamental form, which are allied to the normal section zeta as this equation. Further, we write phi x equals to tx plus mx and phi zeta equals to t dash zeta plus n dash zeta, where tx and t dash zeta, nx and n dash zeta are the tangential and the normal parts respectively. Based on equation 5, the submanifold M classifies as anti-invariant if t equal to 0 or invariant if n equal to 0. The submanifold M of a para-Kenmotsu manifold M bar is termed as involutive if this condition holds, totally umbilical if for any tangent vector field xy it satisfies with equation 7, totally geodesic if h vanishes identically, and minimal if the trace of h vanishes identically. Now the proposition, assume that M be an pseudo-Riemannian submanifold tangent to the structure vector field xi of a para-Kenmotsu manifold M bar, then the relation this holds on M. Assume that the M be a pseudo-Riemannian submanifold normal to the structure vector field xi of a para-Kenmotsu manifold M bar, then the equation this holds in M. Now the slant submanifold, an asymmetrically immersed submanifold M of an almost paracontact manifold M bar is called slant if the quotient this is constant for any time-like or space-like tangent vector field x. Now the theorem, an asymmetrically immersed submanifold of para-Kenmotsu manifold is slant if and only if there exists a constant lambda such that t square equals to lambda I minus eta xi. In particularly, lambda can take any of these three values. Now the next theorem, let M be an isometrically immersed slant submanifold of para-Kenmotsu manifold with slant function lambda, then these two equations holds. Now let M be a totally umbilical proper slant submanifold of a para-Kenmotsu manifold. Then first M is one-dimensional submanifold of M bar and the mean curvature vector H lie in a and M lambda. Next theorem, let M be a totally umbilical proper slant submanifold in para-Kenmotsu manifold M bar. Then M is a totally geodesic submanifold if satisfies del x bar h belongs to gamma mu. Next is the PR semi-slant submanifold. An immersed pseudo-Riemann submanifold in a Parakanmotsu manifolds embarked with psi tangent to n is called a pr semi-slant submanifold if its tangent model Tm then orthogonally decomposed as a direct sum of phi invariant distribution dt and a slant distribution d lambda, and the Tm can be written as d lambda plus dt plus xi. Theorem: let M be a pure semi-slant submanifold of a Parakanmotsu manifold.
Miss Divan, please conclude your presentation within 1 or 2 minutes.
Okay, sir. Xi belongs to gamma dt, then the distribution dt is totally geodesic if this condition hold and integrable if this condition hold. And the pure semi-slant submanifold of Parakanmotsu manifold, then the distribution d lambda is totally geodesic if this condition holds and integrable if equation 14 holds. The distribution dt is totally geodesic if this condition holds and integrable if equation 16 holds if xi belongs to gamma d lambda. And the distribution d lambda is totally geodesic if 17 holds and integrable if 18 holds for xi belongs to gamma d lambda. An isometrically pseudo-Riemann semi-slant submanifold of a Parakanmotsu manifold is named as mixed totally geodesic if h dt d lambda equal to 0, and this is the result regarding this. And these are the references. Thank you.
Okay, thank you. So if anybody wants to ask the questions, you can ask. Okay, I think no. So I'm inviting the next participant, Payal Karmakar and Arindam Bhattacharya, Jadavpur University, Kolkata, and their paper presentation title is Cauchy Hemi Slant Some Manifolds of Metallic Riemann Manifolds. So,
Am I audible?
yes, Payal, audible. Okay, you can share your presentation.
Okay. So is my screen visible?
No. Payal, you can try
No.
again. Yes.
Okay.
Payal, please share your screen. Hello.
Hello, am I audible?
Yes, you are audible. Please share your screen.
Is my screen visible?
No. Try again.
One minute, please.
Okay.
I think there is some problem.
Dr. Anup, you can
Yes.
invite next candidate.
Okay, sir.
Let her circle.
Okay. So I'm inviting the next participant, Mohammad Salman, Aligarh Muslim University, Aligarh, and his paper presentation title is Curvature Inheritance in Leaky Flat Space-Time. So, Mr. Salman, you can share your screen and present.
Yes, may I audible?
Yes, you are audible.
Yes.
So is my screen visible?
Payal, please wait.
প্রবলেম
No,
হচ্ছে বুঝতেই
after the
পারছি
after Salman, you
বারবার
can
হ্যাঁ
present. Okay, Payal.
বারবার খালি অসুবিধা হচ্ছে বারবার চেষ্টা করছি কিন্তু হচ্ছে না
Payal.
আরে কি জানি কি প্রবলেম হচ্ছে চেষ্টা
Payal.
করছি হচ্ছে না
Payal, you will try later, okay? Let Mohammed first speak.
Yeah. Yes. Yes.
Yes. Payal, you try
Payal.
am I
afterwards.
audible
Payal, you are audible, but please wait. है ना?
hello am I audible
Yes. Yes. You are audible.
Yes, you are audible, but please, Mohammed will start now. Mohammed.
Mohammed
give chance
Salman
to Mohammed.
will start, and after
Yes.
Mohammed Salman, you can start.
hello
Okay,
am I
Payal.
audible
Payal.
yes am I audible
Yes, you are audible.
Yes, you are audible. You will speak next, okay? Please
Payal.
leave now. Payal,
yes yes
please leave now. First, Mohammed
Okay.
will speak, then afterwards you will try, okay? Wait for
Oh,
wait for 10 minutes, okay?
after 10 minutes
Yes. Yes.
Yeah.
Yes.
Yeah.
So Mohammed
Okay,
Salman,
okay.
you can start.
okay
Okay. Yes.
Yes, your screen is visible, so you can
Visible.
start. Yes.
Yes. I, Mohammed Salman, from Department of Mathematics, Aligarh Muslim University, Aligarh. Today I present my paper, Curvature Inheritance in Ricky Flat Space-Time. It is now divided in three parts. First part is introduction and preliminaries, and second is the proof of the theorems, and third one is the give example for who is satisfying the curvature inheritance and Ricky flat space-time. And then abstract is in this paper I studies the curvature inheritance in Ricky flat space-time, that is the empty space-time, which first one is give example theorem, which is existence possibilities of conformal motion are imitated by the Ricky flat spacetime with curvature inheritance, which is not Petrov type of n. And another one is curvature inheritance inhibited by the plane oriented gravitational wave found. In general theory of relativity, the curvature tensor characterizes the gravitational field into two parts. First, matter part, and second one is the gravitational free part. The interaction between the matter and gravitational part is described by the Bianchi identity. If gravitational physics, the main objective of all investigation is the construction of the gravitational potential satisfying the Einstein field equation is given by the 1.1 equation, which Rij is minus half Rij plus say sigma Gij is equal to k Tij, where Tij is the energy momentum tensor and sigma is the cosmological constant. And assume in this paper assume that cosmological constant is 0 for a given distribution of matter, the achieved by the imposing symmetries on geometry compatible with the dynamics of chosen distribution of matter. The geometrical symmetries of the space-time are representable through the following equation: the derivative of any or geometrical or physical object is equal to twice time more omega multiplied by that. The here Lj is represent the Lie derivative of with respect to the vector field I, and this vector field is may be time like space like normal, where is the denotes the geometrical or physical quantity, and sigma is the scalar. If say here now a simple example can be provided here as a metric inheritance symmetry, that is A is replaced by Gij. Gij is a metric tensor of a Riemannian space before Gi or space time manifold. Is if sigma is 0, then equation 1.2 represent the motion of space-time manifold, which is also this equation is known as Killing equation, which and that vector is satisfy the equation 1.2 is called Killing vectors. Till this, more than 30 symmetric symmetries have been found in the literature for a comprehensive analysis of symmetry inheritance, and the related result is given in the reference 1 and 2. In 1992, the notation of curvature inheritance was introduced by K.L. Dougal. Curvature inheritance is the generalization of curvature collineation, which was defined by the Kurdzin in 1969. Let V4G be the space-time where V4 is a smooth connected Hausdorff four-dimensional manifold, and G is a smooth Lorentz metric of the signature. This defined on V4. The manifold V4 and metric G are assumed smoothly. Smooth, we shall use the usual component notation in a local chart, and a covariant derivative with respect to the symmetric connection sigma associated with the metric G will be denoted by the semicolon. That is the covariant differentiation is denoted by semicolon, and partial derivative is denoted by comma. A smooth vector field Ji generate a curvature inheritance symmetry if it is satisfy the following equation. Here 1 point shows the 1.3, where Lj is Lie derivative of the Riemann curvature tensor of a Riemannian space V4 with respect to the Ji, and sigma is a inheriting factor or scalar function of the space-time coordinate. Uh, if sigma is zero, there if omega is zero, then Lie derivative of RHIJK is equal to 0, then Chi is said to be the preserve a curvature symmetry on V4, or said to the generate a curvature collineation. The curvature inheritance equation 1.3 can be written in the component form as represent 1.4. A recent literature shows a significant interest in the study of the various symmetries, in particular curvature, Ricci, and projective matter and semi-conformal symmetry. These symmetries arises in the exact solution of Einstein field equation 1.1. There exists a large body of literature on the classification of space-time according to their isometries, group of motion, null tetrad method, spinor, or generating techniques admitted by them. These investigation of symmetries played an important role in the classification of the space-time, giving rise to many interesting results with the useful application. As curvature and Ricci tensor like Riemann curvature tensor and Ricci tensor play a significant role in understanding the geometric structure of metric energy momentum tensor, enables us to understand the physical structure of space-time. Many of difficulties encountered in studying the such symmetries in general relativity are due to the fact that the associated vector field may be constituted in finite dimensional vector space. In this paper, we consider the curvature inheritance symmetry in Ricci flat space-time or empty space-time. That is, the Ricci tensor is vanished on the basis of the null tetrad classification. Many others have investigated such symmetry and have derived several results of geometrical and physical interest to that space-time of general relativity. The application of such inheritance symmetry to the space-time of general is, however, limited by the following theorem. The only curvature inheritance admitted by and Ricci flat spacetime not of vector type are conformal motion. In Google shows that one is a necessary condition for a curvature inheritance tensor is the 2.1, where where Hij is equal to Lie differentiation of metric tensor, and this is the also Kling equation. In order to explore the equation 2.0 space-time relativity, the null tetrad component of equation 2.1 is written explicitly. The resulting equation are solved by the empty space-time or Ricci flat space-time. The algebra being simplified, each vector type of choosing the usual canonical form of the tetrad component of the wild tensor. The calculation are straightforward, and it is found that if space-time of is not of vector type n, where represented by 2.3. If metric tensor of where equation 2.3 define a conformal motion, and so theorem is stated in the introduction is proved. Now next, here for space-time of vector type n is found that where Lie derivative of Gij is equal to 2 phi times Gij plus alpha Lij. Here Lij is Li and Lj are the principal vector of wild tensor, satisfying the condition to give 2.5. The Question now arises as to whether or not empty spacetime of tetrad N can admit curvature coordinate inheritance other than the conformal motion. To answer this question, the curvature inheritance by plane oriented gravitational wave are found these spacetime of tetrad N. The plane oriented gravitational wave is given by the where the metric of the plane oriented gravitational wave can be written in the terms of two real coordinates rho and sigma and as complex coordinate z in the form of this 3.1 where they satisfy the condition 3.2. Now here the null tetrad components of the null tetrad components is Li, Ni, Mi, and where xi is the given notation form under tetrad, the intrinsic derivative as the associated with the tetrad being you can represent the equation 2.3.3, 3.4, 3.5, and spin coefficient is represented 3.6, and non-zero null tetrad component of white tetrad is the canonical form. Is a psi 4 is only non-zero component and accepting are the zero. Equation 2 point can written as this form 3.8.
Mohammed Salman, please conclude.
Yes, sir. Yes, sir. Now, in empty space, in empty space, the while conformal curvature tensor is equivalent to the Riemann curvature tensor, and equation 2.5 and 3.8 now conclude the combined. This represent in equation 3.9. Next, let suppose that twice time of alpha here omega plus say 5 plus omega is equal to half lambda, then null tetrad component of equation 3.9 and equation 3.8 with alpha having insteading 14, substituting the 3.6 and 3.7 into these equation yields with alpha is non-zero, represent equation 3.10, 3.12 and so 18 3. Equation 3.10 and 3.12 to 3.16 can be integrated to give this xi1, xi2 and xi3 and lambda is this. Now here these are references. It's here now a special case here. If equation 3.8 is the manipulated using the separation of variable technique and several cases arises, only one case is discussed here, namely that the corresponding to the third order partial derivative with respect to z is 0, and which is also known as plane gravitational wave. In this cases, the coordinate system can be chosen so that this h is equal to this, and xi1, xi2, and xi3 are this. These are references.
Okay, fine. Miss Payal Karmakar. Payal, are you
Yes, am I
there?
audible?
Yes, yes, you are audible. So you can share your screen and present. Mohammed Salman.
Yes. Yes, sir.
Hello. Am I audible? Hello.
While you are audible, please share your screen.
Salman, please mute yourself.
Payal, up. Payal. So I'm inviting the next speaker, Gauri Shankar, Jaspreet Kaur, and Seema Jagir, Central Institute of Punjab, and their presentation title is on the class of homogeneous quark. Quartic Pincelal matrix. Seema.
Yes, sir.
Jasprit, you
Yes,
can
sir.
share your screen.
Okay. Sir, is my screen visible?
Yes, yes.
Okay. Good afternoon, all of you. I am Jasprit Kaur, doing PhD.
Hello, excuse me.
Payal, please wait. After Jasprit, you
Sir,
can start.
please give me one chance.
Okay, but please wait.
Actually,
After Jasprit, you can share your screen. Okay?
okay.
Shall I start, sir?
Jasprit, yes, yes.
Okay. I am Jasprit Kaur, doing PhD under the supervision of Professor Gauri Sankar, Central University of Punjab. Today, title of my talk is on the class of homogeneous quadrant functional metric admitting alpha beta type. Contents of my presentations are overview, introduction, primarily homogeneous Jurassic and homogeneous quadrant functional metric, natural reductor homogeneous quadrant functional spaces with the quadrant metric, and flag curvature of a homogeneous quadrant functional spaces, and last reference. Overview. In this talk, we study Jurassic and Jurassic vectors for a homogeneous quadrant functional matrix admitting alpha beta type. Then we prove that the necessary and sufficient condition for a non-zero vector in the alpha set metric to be a Jurassic metric. Next, we prove that the two definitions given by Dangan and Latifi for a natural vector homogeneous functional spaces are equivalent under the Medley condition for alpha Z metric. Finally, we derive the formula for the flag curvature of a homogeneous quadrant Finser spaces. Introduction. Finser spaces is named after Paul Finser, who studied it in his doctorate thesis in 1917. Finser's geometry is just a Riemannian geometry without the quadrant restrictions. In Riemannian geometry, restriction of the metric to the tangent space is the inner product, but in the Finser space, so their tangent spaces at different points are linearly isomorphic to each other. But in the Finser space, tangent spaces at each points are can be very different. So when we think about a Finser manifold, we we think about a Finser's manifold where the inner product does not only depend on where you are, but also in the direction where you are looking for. And there are two important classes of Finser metric, namely the class of alpha beta metric and the mth root metric. A Finser metric F that is equal to alpha phi S, where S is beta upon alpha, where phi is a smooth function, alpha is a Riemannian metric, and beta is one form on a Finser manifold is called alpha beta metric. The important and interesting examples of alpha beta metrics are random metric, Kropna metric, Matsumoto metric, infinite series metric, generalized Kropna metric, etc. The theory of mth root metric has been developed by Shimada as an interesting example of Finser metric in 1902 and 1903. The mth root metric has applied to beginning theoretical physics. Let Mn be the smooth manifold of space n and Tm it is a tangent bundle. Then the mth root metric is defined by f that is equal to under root of mth under root of a, where a I1, I2, so on, Im is symmetric in all its indexes. The third root metric is called the cube metric, and the fourth root metric is called quadrant metric. The special mth root metric where a is equal to a, I1, I2, so on, Im is equal to 1 is called the Brevard-Morrow metric. The theory of mth root metric play an important role in physics, gravitation, space-time structure theory, seismic ray theory, and general relativity. Lee and Shena investigated the geometrical property of fourth root locally projective metrics. Kim and Parker introduced the mth root metric which admitting alpha beta type. And Tabi and Jeffy have investigated locally donut flat mth root Finser metrics and mth root Brevard metrics. Next, the Jurassic of the homogeneous existence of the homogeneous Jurassic and commuting flag curvature on homogeneous Finser manifolds are interesting and important example problems in Finser geometry. If a Jurassic is an orbit of one-dimensional parametric group of isometric of a Finser manifold, then it is called homogeneous Jurassic. Flag curvature is in a functional geometry is a generalization of Riemannian geometry section curvature. The amount that Riemannian manifold developed from the Euclidean space is called the is defined by the terms of sectional curvatures. In 1926, Brevard introduced the notation of a flag curvature. In literature, there are two different definitions of natural vector spaces. The one is given by Deng and Hu, and the other is given by Latifi. Deng and Hu has proved that if the homogeneous Pincer space is a natural vector by Latifi's definition, then it must be a natural vector by Deng and Hu's definition and Brevardian. Next are some definitions which we use to prove our results. First is Pincer manifold. A Pincer manifold is a smooth manifold with a Pincer space f from a Pincer metric f t from Tm to 0 to infinity, where f is smooth function on slight tangent when f is positive homogeneous and its rational
Hello.
vector is positive defined. Yes, sir.
Jasprit, I think you should come to your main findings, which is already.
Okay, sir. Okay, so there are some definitions which we use. Yes, sir. There are some definitions which we use. And our main result is let H be a closed subgroup of a compact Lie group G and GHF be a homogeneous Pincer space with coordinate metric. Then let A tilde be an invariant Riemannian metric on a homogeneous Pincer spaces and X tilde be an invariant vector field such that X is equal to X tilde. Then X is a Jurassic vector of G by H A tilde if and only if it is a Jurassic vector corresponding to the Pincer space. To prove this result, first we take a written the coordinate metric in the form of alpha beta, Riemannian metric, and one form. So after that we find it is G by X Y by this formula value of this is the calculation which we do, and then we find to prove that X is a Jurassic vector, we find Gx Lie vector of X Z X that can be written in the form of 1 by F square C1 A tilde XY plus so on this. So here we get if Gx Lie vector of XZ X is equal to 0, then A tilde XZ is equal to 0. So if it is Jurassic with respect to a Riemannian metric, then it is also Jurassic with respect to the Pincer space. Our next result is for we prove the Jurassic condition for any non-zero vector y under such that 2c1 a tilde y plus 2c a tilde x y square not is equal to 0 and a tilde x Lie vector of y z is equal to 0. Yes, sir. Yes,
Please conclude
okay,
your
sir.
presentation within 2 minutes.
Okay, sir. So here we again using the metric gy yx uv find the value of this, and here we get if y is a Jurassic vector of corresponding to Riemannian metric, then it is also Jurassic vector corresponding to Pincer space. Next, in this theorem, we prove that the two definitions given by Deng and Hu and Latifi are equivalent. So here we prove if it is a natural vector corresponding to Pincer space, then then it is a natural vector with respect to the Riemannian space metric. So here first we use the definitions of Riemannian metric to be a natural vector, then use it and find some calculations. And then we after this we calculated Cartan tensor, and here we prove that it is also natural vector with respect to the Pincer space. In the converse part, we let it is a natural vector with respect to the Pincer spaces. Then take it for any v, find the value of g by Lie vector y u v plus this, and then prove that it is also natural vector with respect to the Riemannian metric. And in the second last theorem, we prove that if f is coordinate metric arising by the invariant Riemannian metric, then it is flag curvature is defined in the form of equation 16, where a is equal to this, y b is equal to this, and c is equal to this.
Again, here we find the value of g y y g u minus g y u square, and then put these values in the formula of flat curvature and find its formula. And the last theorem is, here we find the flat curvature for the natural reductive homogeneous Finster spaces. So we use the formula of the Riemannian curvature for the natural reductive Finster spacing using in the Wabb theorem, and we get the formula for the flat curvature of natural reductive homogeneous Finster spaces. These are my reference. Thank you.
Okay, fine. Just breathe. So if anybody wants to ask the questions, you can ask. I think no questions. So Miss Payal Karmakar, are you there? Payal? Payal? I think she is not available.
Call the next.
Okay, so I'm inviting the next participant, Kaushik Chattopadhyay and Arindam Bhattacharya and Sampa Pahal.
Am I audible?
Yes, you are audible.
Hello.
Yes,
Okay.
yes. So you can share your screen and start. Kaushik.
Yes. So can my screen be seen?
Yes, yes. It's visible. You can start.
Okay. Good evening, everyone. I am Kaushik Chattopadhyay, and I am here to talk about on some general relativistic perfect fluid mixed quasi-instant spacetimes application. So this is the overview of our research work. Here we have proved that a Ricci symmetric perfect fluid mixed quasi-instant spacetime is actually a generalized Robertson-Walker spacetime, and it also becomes something more. That is a Robertson-Walker spacetime if it satisfies the Einstein field equation without cosmological constant. Moreover, the flow becomes irrotational and also geodesic. Finally, we have also found out the Ricci-Soliton structure in such spacetime, and we have also concluded our work by giving a non-trivial example of the mixed quasi-Einstein spacetime. Now, these are some of the definitions in introduction that I will not waste much time. That just the definitions of all the manifolds and all the structures that we have used in our research work, including the nearly quasi-Einstein manifold, mixed quasi-Einstein manifold, the nullity distributions definition. Then it is the perfect fluid spacetimes definition. Here is that this Txy is the energy momentum tensor, and that is defined in the fashion of sigma plus p into ax plus ay plus p into g xy. Here sigma stands for the energy density and p stands for the isotropic pressure of the spacetime. And now this is the famous Einstein field equation, and this is with cosmological constant. You can see a lambda is there in the third term. That is sxy minus r by 2 gxy plus lambda into gxy. That lambda represents as the cosmological constant. If we remove that term, still the equation satisfies the criteria, but without the cosmological constant term. Now in our work, we have used both the equations of with lambda and without lambda, that is with cosmological constant and without cosmological constant, and concluded the results out. Now this is the Levi-Civetta connection or the Riemannian connections definition, and this is the same. These are also some of the few definitions that we have used. These are the curvature tensors that we have used in our research work. This is the semi-conformal curvature tensor, to be very specific, that we have used. The importance of this curvature tensor is that it is the combination of two possible tensors. One is the conformal curvature tensor, and second one is the conharmonic curvature tensor, both of which are extremely crucial in differential geometry to discuss the topics out there. And since being a combination of those two tensors, it also plays an important role in studying the topics of differential geometry. So here is the definition of the Ricci-Soliton. The Ricci-Soliton structure, the equation is given there. That is S plus half into LVG plus lambda g equals to 0. And so these are our results. First set of results. These are the theorems that we have used actually. These are the theorems we have used in our research work. The first theorem A and theorem B, they were previously derived by Sir S.K. Chaube, and the third theorem was derived by Shipley and Tau, theorem C. These theorems we will use in our research work. Here in the first theorem, we have proved that the mixed quasi-Einstein spacetime, which we were supposed to discuss about, is the W1 curvature tensor is actually divergence free. And then we have used the theorem B to conclude the theorem 2, because the theorem B states that a perfect fluid spacetime with divergence free W1 curvature tensor is a GRW spacetime, and in our spacetime we have proved that the spacetime becomes W1 divergence free. That is, we have used that result to conclude the theorem 2, that is the Ricci symmetric perfect fluid mixed quasi-Einstein spacetime is indeed a generalized Robertson-Walker spacetime. Now, using this in our next slide, we have used one more theorem, that is here it was previously proved by Sir UC De, A.L. Dijan, S. Malik, that sigma plus P that becomes 0, that is the summation of the energy density and the isotropic pressure in such spacetime becomes 0. So we can clearly see if we take P, then it will become minus sigma, that is P becomes a function of sigma, P is equal to P sigma,